Welcome to this series of videos where we explore how to define and solve electromagnetic problems. This playlist is designed to take you from the foundational concepts of electromagnetism to advanced applications, particularly in the field of brain imaging. In this first video, we lay the groundwork by introducing key mathematical concepts essential for understanding electromagnetics. We will dive into vector analysis and the mathematical formulation of electromagnetic waves, which are crucial for grasping how electric and magnetic fields interact and propagate. We'll explore the following topics: vector fields and linear algebra, how they form the backbone of electromagnetic theory; Maxwell's equations, an introduction to the differential and integral forms that govern electromagnetic phenomena; electromagnetic wave formulation, the basics of how waves are mathematically described and how they propagate through space. This foundation will prepare you for the upcoming videos, where we'll discuss the radiation of electromagnetic waves, their propagation through different materials, and apply these principles to real-world problems, including brain tissue analysis and imaging. To delve into computational electromagnetics, we begin with Maxwell's equations. These equations form the foundation of electromagnetic theory and consist of four fundamental equations, which are represented on the left side of this slide in both differential and integral forms. Their concepts are also visualized schematically. Maxwell's equations are: 1. Gauss's law for electricity describes the distribution of electric charge and the resulting electric field. 2. Gauss's law for magnetism states that there are no magnetic monopoles, hence, magnetic field lines are closed loops. 3. Faraday's law of induction indicates that a changing magnetic field induces an electric field. 4. Ampere's law, with Maxwell's addition, relates the magnetic field to the electric current and changing electric fields. From these four equations, we can derive the nature of time-varying vector fields and electromagnetic waves. Specifically, Maxwell's equations show how electric and magnetic fields propagate as electromagnetic waves. These equations consist of two related to electric fields and two related to magnetic fields. To fully understand these phenomena, we will explore vector analysis and the fundamental principles of electromagnetic waves as time-varying vector functions from a mathematical perspective. This includes deriving wave equations, such as the hyperbolic wave equation, and understanding Poisson's equation in the context of electromagnetism. By analyzing these equations, we gain insights into how electromagnetic waves propagate, interact, and how they can be modeled mathematically. Vector fields and linear algebra are indispensable tools for understanding and solving problems related to electromagnetic phenomena, particularly through the application of Maxwell's equations. These mathematical concepts allow for a deeper comprehension of how electric and magnetic fields behave across various physical situations. Vector fields are fundamental in electromagnetism, representing the distribution of vector quantities, such as electric and magnetic fields, across space. These fields are analyzed using key vector calculus operations: gradient, divergence, and curl. The gradient measures the rate of change in a scalar field, like electric potential. The divergence identifies sources or sinks within a vector field, such as charge distributions generating electric fields. The curl describes rotational properties within a vector field, crucial for understanding magnetic fields generated by moving charges or currents. These operations form the backbone of Maxwell's equations, which are typically expressed using vector calculus notation. These equations govern electromagnetic theory, describing how electric and magnetic fields propagate and interact. On the right-hand side of the slide, figures illustrate fundamental vector operations: unit vectors, dot product, and cross product. The dot product helps us understand the projection of one vector onto another, which is essential for analyzing fields like electric fields in specific directions. The cross product results in a vector perpendicular to the original two vectors, crucial for understanding phenomena like magnetic force and torque. Linear algebra plays a significant role in electromagnetism by providing the framework for solving the complex systems of equations arising from Maxwell's equations. Concepts like matrix operations, eigenvalues, and eigenvectors are particularly useful in more complex scenarios, such as analyzing electromagnetic fields in anisotropic media or solving boundary value problems. Together, these mathematical tools, vector calculus and linear algebra, allow us to model, understand, and solve real-world electromagnetic problems effectively. They enable a detailed analysis of how electric and magnetic fields are distributed, how they interact, and how they propagate through space, providing the foundation for much of modern electromagnetic theory. In this slide, we delve into the fundamental operations of vector calculus, gradient, divergence, and curl, within a vector field, exploring how these operations help us interpret the behavior of fields. Additionally, we will introduce the Helmholtz decomposition, a powerful theorem that breaks down any sufficiently smooth vector field into three distinct components. The gradient of a scalar field points in the direction of the greatest rate of increase. A zero gradient indicates no change in field intensity, a positive gradient signals an increase, and a negative gradient marks a decrease. Visualizing these scenarios, imagine a flat plateau where the scalar field, such as electric potential, is uniform. This represents a zero gradient. A hill where the field increases as you move up illustrates a positive gradient, while a valley, where the field decreases as you move down, represents a negative gradient. The divergence measures how much a vector field spreads out or converges at a point. A zero divergence implies no net outflow or inflow, a positive divergence suggests a source where the field is spreading out, and a negative divergence indicates a sink where the field is converging inward. For example, visualize a uniform fluid flow where the same amount flows in and out at any given point. This shows zero divergence. Air being blown out of a fan, where field lines radiate outward, represents positive divergence, while water draining into a sink, where field lines converge, illustrates negative divergence. The curl represents the rotational tendency of the field around a point. A zero curl indicates no rotation, while a positive curl signifies counterclockwise rotation, and a negative curl indicates clockwise rotation. To visualize, consider a calm river flowing straight with no swirls, representing zero curl. A whirlpool spinning counterclockwise demonstrates a positive curl, whereas a whirlpool spinning clockwise shows a negative curl. These operations are interconnected through key mathematical relationships. The curl of the gradient of any scalar field is always zero, meaning that there is no rotational component in the direction of the steepest ascent or descent. Similarly, the divergence of the curl of any vector field is zero, indicating that a purely rotational field has no net source or sink. The divergence of the gradient of a scalar field result in the Laplacian, an operator that quantifies the rate at which a quantity diffuses or spreads out from a point in space. The Laplacian is crucial in understanding many physical processes, including the propagation of electromagnetic waves. Finally, the Helmholtz decomposition theorem states that any sufficiently smooth vector field can be decomposed into three components: a gradient field, irrotational component, that is curl-free and associated with the scalar potential of the field, a curl field, solenoidal component, that is divergence-free and associated with the vector potential, and a harmonic component that is both divergence-free and curl-free. This harmonic component represents a field that neither originates from a source nor has rotational tendencies, often linked to boundary conditions or external constraints. Understanding these operations and their decomposition is crucial in electromagnetics, as it allows us to break down complex vector fields into simpler, more manageable components. By analyzing these components individually, particularly in the context of electromagnetic fields, we can better understand and solve complex problems involving the interactions of electric and magnetic fields in space. In this slide, we explore the foundational theorems in vector calculus, Green's theorem, Stokes' theorem, and the divergence theorem, and their applications to line, surface, and volume integrals of vector fields. These theorems provide essential tools for understanding and solving complex problems in electromagnetics and other fields by relating different types of integrals. Green's theorem is a general theorem in vector calculus that relates a line integral around a simple closed curve to a double integral over the region enclosed by the curve. This theorem has two forms. First form, circulation form. This form connects the line integral of a vector field around a closed curve to the integral of the curl of the field over the area enclosed by the curve. It states that the circulation of the vector field around the boundary is equal to the sum of the rotational effects, curl, over the region. Second form, flux form. This form relates the line integral of the field's normal component along the boundary curve to the integral of the divergence of the field over the enclosed region. It tells us that the total flux through the boundary curve is equal to the net source or sink, divergence, within the region. Stokes' theorem is a specific case of Green's theorem applied to a surface in three dimensions. It relates the surface integral of the curl of a vector field over a surface to the line integral of the vector field around the boundary of that surface. Essentially, Stokes' theorem simplifies the evaluation of surface integrals by converting them into line integrals around the surface's boundary. This theorem is crucial for analyzing magnetic fields and circulation effects in three-dimensional space. The divergence theorem, also known as Gauss's theorem, connects the flux of a vector field through a closed surface to the volume integral of the divergence of the field within the enclosed volume. It asserts that the total outward flux through a closed surface equals the sum of all sources or sinks, divergence, within the volume. This theorem is particularly useful in electromagnetics for calculating quantities like total charge or mass by analyzing the field's behavior on the surface and within the volume. Integrals in vector calculus are deeply interconnected. The line integral evaluates the vector field along a curve, capturing quantities like circulation. The surface integral measures the flux of the vector field through a surface, essential for applying Stokes and Green's theorems. The volume integral calculates quantities like total charge within a volume, relevant for applying the divergence theorem. Green's theorem, in its general form, encompasses both the circulation and flux forms, with Stokes' theorem being a special case that extends this idea into 3 dimensions. The divergence theorem bridges surface and volume integrals, showing how flux through a surface relates to divergence within the volume. By understanding these relationships and their integral forms, we can effectively use these theorems to simplify and solve complex vector field problems, gaining deeper insights into the behavior of electric and magnetic fields and their interactions in various physical scenarios. In this section, we'll explore the fundamental role of boundary conditions in electromagnetics, which are essential for understanding how electromagnetic fields interact with surfaces and interfaces between different media. These boundary conditions are not just theoretical. They are directly derived from Maxwell's equations, the cornerstone of electromagnetic theory. By carefully applying Maxwell's equations at the interfaces between different materials, we can extract the specific boundary conditions that the electric and magnetic fields must satisfy. This process ensures that the fields behave correctly at the boundaries, a crucial aspect when solving real-world electromagnetic problems. One key boundary condition is the continuity of the tangential components of both the electric and magnetic fields. At the boundary between 2 different media, these tangential components must remain continuous. This means that the parts of the fields parallel to the boundary cannot undergo sudden changes, which ensures that the electromagnetic fields transition smoothly from one medium to another. This smooth transition prevents any unrealistic discontinuities in the behavior of the fields. On the other hand, the normal components, the parts of the fields perpendicular to the boundary, can experience discontinuities. These discontinuities are related to surface charge and surface current densities. For instance, the normal component of the electric displacement field may jump by an amount proportional to the surface charge density at the boundary. Similarly, the normal component of the magnetic flux density can be influenced by surface currents, causing a discontinuity. To help visualize these concepts, we've included figures illustrating different scenarios of boundary conditions. These images will show how the fields behave at boundaries under various conditions, such as when transitioning from a conductive material to a dielectric, or when encountering surface charges and currents. By seeing these examples, you'll better understand how to apply boundary conditions in practical situations. Grasping these boundary conditions is essential for accurately modeling and analyzing the interactions of electromagnetic waves with various materials and interfaces. Whether you're designing antennas, waveguides, or studying how electromagnetic fields propagate through complex media, mastering these conditions will ensure that your solutions are both accurate and physically meaningful. Now that we've covered the fundamental boundary conditions, let's move on to a critical concept in electromagnetics, the uniqueness theorem and the duality of electromagnetic fields. On the left side of the slide, we see the uniqueness theorem, which states that if the boundary conditions and sources of an electromagnetic problem are well defined and satisfy Maxwell's equations, the solution to the fields within the region is unique. This is a powerful result because it assures us that the fields we calculate, given the correct boundary conditions, are the only possible solution for that scenario. The reliability of our solutions in complex electromagnetic problems, such as those involving antennas, waveguides, or imaging, is guaranteed by this theorem. Directly tied to this is the concept of duality in electromagnetics. Duality refers to the symmetry between electric and magnetic fields in Maxwell's equations. For every electric field scenario, there's an analogous magnetic field scenario. This symmetry simplifies the analysis of complex problems, as it allows us to switch between electric and magnetic perspectives depending on which is more convenient for the problem at hand. On the right side of the slide, you'll notice a schematic illustrating this duality through 2 examples: the image theorem for a perfect electric conductor and the equivalent model for a magnetic source near a conductor. The image theorem, shown here, demonstrates how the fields generated by a real source can be replaced by an imaginary or image source inside a perfect conductor, allowing us to simplify the problem while maintaining the correct boundary conditions. Similarly, the equivalent model illustrates how a magnetic source near a conductor can be modeled using equivalent electric sources to simplify the problem. These examples highlight the practical application of the uniqueness theorem and boundary conditions. By ensuring that we define our boundary conditions correctly, we can confidently use these models and theorems to solve complex electromagnetic problems. Whether we're dealing with electric or magnetic fields, or applying the image theorem to simplify a situation, the uniqueness of our solution is guaranteed as long as our initial conditions and boundaries are well defined. As we conclude this session, let's explore some important equivalence principles in electromagnetics, illustrated here on this slide. On the left, we see an illustration of the surface equivalence principle. In this scenario, we have an imaginary closed surface with impressed electric and magnetic current sources, represented as Js and Ms in the original problem, shown in part A. We have the true source distributions inside the surface, denoted by J1 and M1. The equivalent problem, depicted in part B, shows how these sources can be replaced with equivalent sources on the surface S. This replacement yields the same external electric and magnetic fields as the original problem, while the internal fields and surface currents are adjusted to enforce the correct boundary conditions. This principle is essential in simplifying complex field problems, reducing them to surface integrals without altering the external field distribution. On the right, we have an illustration of Love and Shelkonov's equivalence principles. Starting with part A, we have the original problem. Part B shows Love's equivalent problem, where the fields inside the region are replaced with equivalent surface sources, ensuring that the external fields remain unchanged while the internal fields are adjusted. Parts C and D show Shelkonov's equivalent problems, part C with a perfect electric conductor and part D with a perfect magnetic conductor. In both cases, the external fields remain the same as in the original problem, but the internal sources and boundary conditions are chosen to match the physical constraints of the conductors. These illustrations clearly demonstrate how the equivalence principles allow us to transform complex electromagnetic problems into more manageable forms without altering the external field behavior. By understanding and applying these principles, we can greatly simplify the analysis and design of electromagnetic systems, especially in antenna theory and waveguide design. With this, we bring today's video to a close. In the next session, we will build upon these concepts by exploring the principles of electromagnetic radiation and propagation, diving deeper into how these equivalence principles can be applied in practical scenarios. Thank you for watching, and I look forward to seeing you in the next video. Welcome to the second video in our series on computational electromagnetics theory. In this video, we're going to dive into the fascinating topic of electromagnetic radiation, a cornerstone of modern physics and engineering. Electromagnetic radiation is all around us, from the light we see to the radio waves that power communication systems. It's the mechanism by which energy is transferred through space via oscillating electric and magnetic fields. Understanding how these waves are generated, propagate, and interact with matter is essential for anyone working in fields like telecommunications, radar, and even medical imaging. Throughout this video, we'll explore the fundamental principles governing electromagnetic radiation, beginning with how electromagnetic waves are generated and evolve as they travel through space. We'll also discuss the foundational theories and principles that explain the behavior of these waves, including waveforms like sinusoidal and standing waves, and how they are described by Maxwell's equations. By the end of this session, you'll have a deeper understanding of the nature of electromagnetic radiation and how it applies to real-world technologies. So, let's get started and explore the fascinating world of electromagnetic radiation. On the left side of the slide, you can see an animation of a dipole generating electromagnetic waves, illustrating how an oscillating dipole produces time-varying electric E and magnetic B fields. These fields are governed by Maxwell's equations, which are also depicted next to the dipole. As the charges in the dipole oscillate, the resulting time-varying E and B fields interact and propagate outward, forming electromagnetic waves. To understand how these fields evolve into traveling waves, let's look at the right side of the slide, which breaks down this process over time, t=0. Initially, the dipole starts oscillating, generating the first E and B fields. At this moment, the fields are primarily concentrated near the dipole, with complex interactions beginning to emerge. Time equals 0.25 to time equals 0.5. As time progresses, the fields begin to propagate away from the dipole. They are still relatively close to the source, with the wavefronts not yet fully formed, showing complex patterns typical of the Fresnel region, near field, where the fields are strong and highly interactive. Time equals 0/75 to time equals t. By the time we reach time equals t, the fields have transitioned into a well-defined traveling electromagnetic wave, moving away from the source. This is characteristic of the Fraunhofer region, far field, where the wavefronts are planar and the fields are less complex, having evolved into a stable propagating wave. This slide illustrates the entire process, from the initial creation of E and B fields at the dipole to their evolution into traveling electromagnetic waves. Understanding this time evolution is crucial for grasping how electromagnetic waves propagate in free space, and how they transition from complex near-field interactions to the simpler far-field radiation patterns. As we continue to delve into the fundamentals of electromagnetic wave propagation, let's first focus on the left side of the slide, where we have the Poynting theorem in its integral form. This theorem is crucial as it mathematically expresses the conservation of electromagnetic energy within a given system. The integral form of the Poynting theorem is shown here, which relates the rate of energy transfer through a surface to the electromagnetic fields within a volume. In this equation, S is the Poynting vector, E is the electric field, and J is the current density. This integral formulation emphasizes that the Poynting vector S equals E cross dot H isn't just a theoretical construct, but a tangible measure of how electromagnetic energy moves through space. By integrating over a surface, we can determine the total power passing through that surface, and by considering the volume, we can understand how energy is distributed and conserved within that region. On the right side of the slide, we delve into the radiation zones and wave fronts, key concepts that further describe the behavior of these electromagnetic waves as they propagate. In the near-field Fresnel zone, which is close to the source, the wave fronts are spherical, illustrating the complex interaction of electric and magnetic fields that are tightly bound to the source. The Poynting vector in this region can be highly variable, reflecting the intricate energy distribution and the reactive nature of the fields. As we move into the far-field, Fraunhofer zone, the wave fronts straighten out and become planar. Here, the Poynting vector indicates a more uniform and stable flow of energy, aligned with the direction of wave propagation. This is where the waves have transitioned into a simpler form, making it easier to analyze their long-distance behavior. By understanding the Poynting theorem and its integral form, alongside the characteristics of wave fronts and radiation zones, we gain a comprehensive picture of how electromagnetic energy is generated, transferred, and conserved as it travels through space. As we continue our exploration of electromagnetic waves, let's delve into the concept of time harmonic electromagnetic waves and their role as solutions to the source-free Maxwell's equations. These equations are fundamental in describing how electric and magnetic fields propagate through free space when there are no charges or currents present. Now, on this slide, you can see the source-free Maxwell's equations, which govern the behavior of these fields. When solved under time harmonic conditions, these equations give rise to the wave equations that describe how these fields oscillate and propagate. Time harmonic waves are characterized by their sinusoidal variation over time, a key feature that simplifies our understanding of wave phenomena. To help visualize this, we've included a schematic that shows these waves and their relevant parameters. Additionally, we've illustrated the different waveforms that time harmonic waves can take. First, we have the sinusoidal waveform, which is the most basic and fundamental form. This waveform oscillates smoothly in both time and space, providing a clear and simple picture of wave behavior. Next, we look at standing waves. These are formed by the superposition of two traveling waves of equal amplitude and frequency, moving in opposite directions. The result is a stationary pattern with fixed nodes, where the wave amplitude is zero, and antinodes, where the amplitude is at its maximum. This pattern is particularly significant in resonance systems and cavities, where understanding and controlling wave behavior is crucial. By exploring these waveforms, we gain a deeper understanding of how time harmonic electromagnetic waves, as solutions to the source-free Maxwell's equations, propagate and interact in free space. This knowledge lays the foundation for further studies and practical applications in electromagnetic theory. Here we continue with aperture radiation, which involves the study of how electromagnetic waves are radiated from an aperture or an opening in a conducting surface. This topic is important for entering the antennas concept and other radiating structures emit electromagnetic waves. It connects well with the previous discussions on wave propagation by showing practical applications and real-world implementations of wave theory. As we move into the topic of aperture radiation, we begin by exploring the volume equivalence theorem. This theorem is crucial in understanding how electromagnetic fields can be represented and analyzed using equivalent sources. On this slide, you'll see a series of figures that illustrate the concept. First, in Figure A, we have the generic original problem, which represents the general scenario with a given electromagnetic field distribution. Next, in Figure B, we see the external equivalence, where the original problem is replaced with equivalent sources that produce the same fields outside a certain volume, while Figure C shows the asterisk internal equivalence, where the equivalent sources produce the same fields inside the volume. These equivalent representations simplify complex electromagnetic problems, making them easier to analyze and solve. Moving forward, we introduce Huygens principle, a foundational concept in wave propagation. This principle states that every point on a wavefront can be considered as a source of secondary spherical wavelets, and the new wavefront is formed by the envelope of these wavelets. On the right side of the slide, you'll see an illustration that demonstrates this principle, particularly how a wavefront emerges from an aperture. As the wavefront passes through the aperture, each point within the aperture acts as a secondary source, radiating wavelets that combine to form a new wavefront. This visualization helps us understand how waves propagate and diffract when passing through openings, which is essential in designing and analyzing antennas, lenses, and other electromagnetic systems. By grasping the volume equivalence theorem and Huygens principle, we build a solid foundation for understanding how electromagnetic waves behave when interacting with apertures, paving the way for more advanced topics like antenna theory. As we conclude this section on aperture radiation, we now transition into the core principles of antenna theory, focusing on two foundational concepts. First, let's delve into Lorentz reciprocity. This principle is the cornerstone of how antennas both transmit and receive electromagnetic waves using the same underlying mechanism. Lorentz reciprocity asserts that the electromagnetic response of a system remains consistent, whether we switch the source and observation points. This symmetry is not just a theoretical insight, it's a powerful tool that simplifies the analysis and design of antennas by providing predictable, symmetrical relationships between transmission and reception. This makes it easier to optimize antenna performance in a wide range of practical applications. Next, we explore the Babinett principle, which plays a crucial role in understanding diffraction and how electromagnetic waves interact with apertures and obstacles. The Babinett principle tells us that the diffraction pattern of an aperture is complementary to that of an obstacle with the same shape and size. This principle is essential for analyzing and predicting wave behavior in various scenarios, especially in complex environments where waves encounter obstacles or apertures. By mastering these principles, Lorentz reciprocity and the Babinett principle, we deepen our understanding of antenna operation and electromagnetic wave behavior, enabling us to design more effective communication systems and other electromagnetic applications. In the next video, we will shift our focus to electromagnetic wave propagation and its interaction with materials, exploring how waves behave as they travel through different media and the implications this has for various technologies. Welcome to this video on electromagnetic propagation, a critical aspect of electromagnetic theory that explains how waves travel through various media. In our previous videos, we explored the basics of electromagnetic radiation and the fundamental principles underlying wave behavior. Now, we'll delve deeper into how these waves propagate through different materials. To fully understand electromagnetic propagation, we must go beyond Maxwell's equations and look at the supplementary constitutive equations. These equations play a vital role in linking the electric and magnetic fields to the properties of the medium through which they travel. Specifically, they incorporate the effects of material properties like conductivity, permittivity, and permeability, which significantly influence how electromagnetic waves move through different substances. In this video, we'll explore how these material properties affect wave propagation, including how they determine the speed, attenuation, and reflection of waves. We'll break down each constitutive equation and discuss how conductivity affects the loss of wave energy, how permittivity influences the electric field's response, and how permeability impacts the magnetic field's behavior. By the end of this session, you'll have a clearer understanding of how electromagnetic waves interact with materials and how these interactions are governed by the constitutive equations. This knowledge is essential for anyone working in fields like material science, telecommunications, and electromagnetic compatibility. So, let's begin our exploration of electromagnetic propagation and the critical role played by material properties. This slide serves as an introduction to the interaction of electromagnetic waves with different material mediums, emphasizing the critical role these materials play in influencing wave behavior. The slide lays the groundwork for understanding how electromagnetic waves respond when encountering various materials such as conductors, dielectrics, and biological tissues. As electromagnetic waves propagate through these mediums, their speed, direction, and intensity are altered based on the material's properties, including permittivity, permeability, and conductivity. These properties govern the wave's reflection, refraction, and transmission. For example, in conductors, electromagnetic waves are primarily absorbed and converted into heat, resulting in minimal transmission. In contrast, dielectrics allow partial transmission of the wave, contingent on their specific properties. The behavior of waves in these different materials is pivotal, especially in complex environments like biological tissues, where phenomena such as complex permittivity and dispersion significantly affect wave propagation. The slide also delves into the mathematical formulation of these interactions, focusing on the role of permittivity within Maxwell's equations and the wave equation. It introduces the concept of the complex propagation constant, which encapsulates both the attenuation and phase shift of waves in a medium, as well as the complex intrinsic impedance, which describes the relationship between the electric and magnetic fields in the wave. Furthermore, the slide highlights the concepts of phase velocity and group velocity, which are fundamental to understanding wave propagation in various mediums. Phase velocity is defined as the speed at which the phase of the wave propagates, calculated as the ratio of the wave's angular frequency to its wave number. This velocity determines how quickly the crests of the wave move through space. Group velocity, on the other hand, refers to the speed at which the overall energy or information carried by the wave packet moves. It is derived from the derivative of the angular frequency with respect to the wave number. This concept is particularly important in dispersive media, where different frequencies travel at different speeds, leading to the spreading of the wave packet over time. The relationship between group velocity and phase velocity is crucial in distinguishing between dispersive and non-dispersive waves. In non-dispersive media, these velocities are equal, meaning all components of the wave travel at the same speed. However, in dispersive media, they differ, which can result in phenomena where the phase of the wave travels at a different speed compared to the overall wave envelope, as illustrated in the diagrams on the slide. This slide serves as a detailed introduction to the concept of complex permittivity, which is essential for understanding how electromagnetic waves interact with various materials. The core idea behind complex permittivity is to describe a material's ability to both store and dissipate energy when subjected to an electromagnetic field. This is represented by the complex permittivity epsilon r omega, which has two components. The real part corresponds to the material's capacity to store energy through polarization, while the imaginary part accounts for the energy lost as heat within the material. Together, these components encapsulate the material's overall electromagnetic behavior. Moving forward, the slide delves into the concept of current density JCD in materials, breaking it down into two key components: conduction current JCE and displacement current JD. The conduction current, JCE, is directly related to the material's electrical conductivity sigma E and represents the energy dissipated as heat, primarily through the movement of free charge carriers like electrons. On the other hand, the displacement current, JD, is associated with the polarization of the material and reflects the energy temporarily stored within it. The total current density JCD is thus the sum of these two components, providing a complete picture of how the material responds to an applied electric field. As the discussion progresses, the slide introduces how different materials, specifically conductors and dielectrics, behave under the influence of an electromagnetic field. In conductors, the conduction current JCE is dominant due to the high electrical conductivity, which means that most of the energy from the electromagnetic field is dissipated as heat. The displacement current JD in conductors is comparatively minimal, indicating that little energy is stored. In contrast, dielectrics are characterized by a dominant displacement current JD, as these materials do not have free charge carriers and primarily store energy through polarization. The conduction current in dielectrics is negligible, resulting in minimal energy dissipation. The slide also features a vector diagram that visually represents the relationship between the displacement current and the conduction current. This diagram illustrates how these two components combine to form the total current density JCD. In this representation, the displacement current is shown as perpendicular to the conduction current, reflecting that they are typically out of phase by 90 degrees. This visual aid reinforces the understanding of how different materials interact with electromagnetic waves, in conductors, where energy loss is predominant, and in dielectrics, where energy storage is the key characteristic. In this slide, we delve into the constitutive equations, which are crucial for linking Maxwell's equations to the material properties that govern electromagnetic wave propagation. These equations describe the interaction between electric and magnetic fields with different materials, influenced by key parameters such as permittivity, permeability, and conductivity. Permittivity epsilon determines how a material responds to an electric field, influencing the electric displacement field. D. Permeability mu governs the material's response to a magnetic field, affecting the magnetic flux density B. For conductive materials, conductivity sigma relates the electric field E to the current density J, which is pivotal in understanding how electric currents are handled within the material. Furthermore, the electric polarization P and magnetic polarization M significantly impact the fields, particularly in dielectric and magnetic materials, by defining their ability to store and dissipate electromagnetic energy. For isotropic materials, these properties are uniform in all directions, simplifying the analysis. However, in anisotropic materials, permittivity and permeability vary with direction, necessitating a tensor-based approach to accurately describe field interactions. Heterogeneous materials exhibit spatially varying properties, requiring more detailed analysis to account for compositional changes across different regions. Heterogeneous materials add another layer of complexity, with spatially varying properties such as permittivity, permeability, and conductivity. These variations demand localized analysis to understand how electromagnetic waves interact with different regions, leading to complex behaviors like reflection, refraction, and scattering. Dispersion is also critical, especially in dispersive materials where permittivity and permeability depend on the wave's frequency. This causes phase velocity to vary with frequency, leading to wave packet spreading and signal distortion. Understanding dispersion is vital for applications like optical fibers and antennas. Electromagnetic wave behavior in both dispersive and heterogeneous materials is characterized by the intricate interaction between the material properties and the wave's frequency and spatial variation. This understanding is crucial for accurately predicting wave propagation and optimizing device performance. On the slide, we've provided all the relevant formulations for conductors and dielectrics, along with schematic representations of isotropic, anisotropic, homogeneous, and heterogeneous materials. These visuals and equations are essential for grasping how electromagnetic waves interact across different material types. In this slide, we delve into the interaction of electromagnetic waves with material boundaries, focusing specifically on conductive surfaces. We will examine two scenarios: normal incidence and oblique incidence of waves on a conductor. The slide presents the relevant equations for the incident and reflected fields by applying boundary conditions for both normal and oblique incidences. Additionally, the total field, which results from the combination of the incident and reflected waves, is also shown in formulaic form. As depicted in the figures, when an electromagnetic wave strikes a conductor at normal incidence, the total wave forms a standing harmonic wave due to the superposition of the incident and reflected waves. In contrast, for oblique incidence, the resulting total wave is a traveling harmonic wave, described by a sinusoidal function. This slide provides a deeper understanding of how electromagnetic waves behave when encountering conductive boundaries, highlighting the differences in wave behavior based on the angle of incidence. This understanding is crucial for applications involving waveguides, antennas, and electromagnetic shielding. Here, we've calculated the total electromagnetic fields in three regions: before the wave reaches the dielectric boundary, within the dielectric slab, and after the wave exits the slab. The formulas for these fields incorporate the reflection coefficient gamma and the transmission coefficient tau at each boundary of the dielectric slab, providing a complete picture of how the wave propagates through the material. Continuing our discussion on the interaction of electromagnetic waves with materials, this slide provides a summary of the schematic representation of oblique wave incidence on a dielectric boundary. The key objective here is to highlight the concept of total internal reflection, which occurs at a specific angle, as governed by Snell's law, shown on the slide. This angle, known as the critical angle, is significant because it allows for the complete transmission of the wave through the dielectric, leading to the phenomenon of waveguiding. In the slide, we have illustrated a dielectric slab, demonstrating how a wave can be fully guided within it, effectively propagating through the material without escaping. This concept is crucial in the design of waveguides, which are used in a variety of applications, from optical fibers to microwave transmission lines. Additionally, the slide briefly touches on other wave material interaction behaviors such as refraction, diffraction, absorption, and scattering. A simple schematic is provided to visualize these interactions, offering a broader perspective on how electromagnetic waves behave when they encounter different types of materials. Given that the focus of our discussion is on wave propagation in biological tissues, particularly the brain, we will delve deeper into these topics in the following slides. Specifically, we will focus on how waves interact with biological tissues by examining the complex permittivity of these materials. This will provide critical insights into how electromagnetic waves propagate through and interact with biological matter, which is essential for applications like medical imaging and therapeutic technologies. To delve into the interaction of electromagnetic waves with biological tissues, we must first examine dielectrics with complex permittivity and dispersive properties. Complex permittivity, denoted as epsilon star, is a crucial constitutive parameter that defines how a medium interacts with an external electric field. It comprises a real part epsilon prime, which represents the energy stored within the material, and an imaginary part epsilon second, known as the loss factor, which quantifies the energy dissipated as heat. The permittivity of a material is typically expressed relative to the permittivity of free space epsilon 0, resulting in the relative permittivity epsilon r equals epsilon prime over epsilon 0. The loss tangent, defined as tan delta equals epsilon second over epsilon prime, indicates the efficiency of the material in storing versus dissipating electromagnetic energy. A higher loss tangent suggests a material is more lossy, which is critical in applications where energy dissipation is either desirable, as in heating, or to be minimized, as in insulating materials. The dielectric response of a material is not instantaneous and varies with frequency, a phenomenon known as dielectric dispersion. Dispersion leads to a frequency-dependent permittivity, where the phase velocity and group velocity of waves differ, especially in dispersive materials. This relationship is governed by the propagation phase constant and angular frequency, with the group velocity v_g and phase velocity v_p determined by how the medium's constitutive parameters change with frequency. A higher loss tangent suggests a material is more lossy, which is critical in applications where energy dissipation is either desirable, as in heating, or to be minimized, as in insulating materials. The dielectric response of a material is not instantaneous and varies with frequency, a phenomenon known as dielectric dispersion. Dispersion leads to a frequency-dependent permittivity, where the phase velocity and group velocity of waves differ, especially in dispersive materials. This relationship is governed by the propagation phase constant and angular frequency, with the group velocity v_g and phase velocity v_p determined by how the medium's constitutive parameters change with frequency. A higher loss tangent suggests a material is more lossy, which is critical in applications where energy dissipation is either desirable, as in heating, or to be minimized, as in insulating materials. The dielectric response of a material is not instantaneous and varies with frequency, a phenomenon known as dielectric dispersion. Dispersion leads to a frequency-dependent permittivity, where the phase velocity and group velocity of waves differ, especially in dispersive materials. This relationship is governed by the propagation phase constant and angular frequency, with the group velocity v_g and phase velocity v_p determined by how the medium's constitutive parameters change with frequency. The slide features 3 illustrative images to enhance understanding. The first image on the left shows a cross-sectional view of the human brain, highlighting various layers and tissue types, such as the scalp, skull, cerebrospinal fluid, CSF, gray matter, GM, and white matter, WM. Each of these components has distinct dielectric properties that affect the overall electromagnetic wave propagation within the brain. For example, gray matter, rich in cell bodies, exhibits different dielectric behavior compared to white matter, which is composed largely of myelinated axons. This heterogeneity leads to complex permittivity profiles that vary with frequency, necessitating the application of the Kramers-Kronig relations for accurate modeling. The second image, centered on the slide, provides a detailed anatomical view of the layers surrounding the brain, including the scalp, diploid bone, dura mater, arachnoid mater, and pia mater. This image emphasizes the multi-layered nature of biological tissues, where each layer contributes differently to the overall dielectric response. The presence of these layers with varying thicknesses and compositions leads to a highly complex interaction with electromagnetic fields, significantly influencing the wave's reflection, refraction, and absorption within the tissue. Understanding these interactions is crucial, especially in medical applications like electromagnetic imaging or therapeutic treatments where precise knowledge of tissue dielectric properties is essential. The third image on the right introduces a conceptual model of wave propagation through layered media, which can be applied to the study of biological tissues. This model illustrates how an electromagnetic wave interacts with different layers, experiencing gain, loss, and phase shifts as it traverses through each layer. The dielectric properties of the tissue layers determine the extent of these effects, which can be analyzed using the Kramers-Kronig relations to predict the material's response over a range of frequencies. Welcome to the fourth installment of our series on computational electromagnetic theory. In this video, we will dive deeply into the computational methods used to solve complex electromagnetic problems, with a specific focus on how these methods apply to microwave brain imaging systems. We will start by revisiting the types of partial differential equations, PDEs, that arise from Maxwell's equations, which describe the behavior of electromagnetic fields. We will explore how these equations are derived and what they mean for electromagnetic theory and its applications. Next, we will introduce several numerical methods that are employed to solve these PDEs, focusing on boundary value problems, BVP, the finite element method, FEM, and the finite difference time domain, FDTD, method. Each method has its strengths and is suited to different types of problems. BVP is often used for solving static or steady-state problems with defined boundaries, FEM is versatile for complex geometries and material properties, and FDTD is particularly powerful for time domain simulations. We will then take a closer look at the FDTD method, which has proven to be highly effective for solving time-dependent electromagnetic problems. We'll cover its formulation, including the discretization of Maxwell's equations and the time-stepping algorithms used to update the electromagnetic fields. Key considerations such as stability, accuracy, and boundary conditions will be discussed in detail. Finally, we will apply the FDTD method to a practical problem, microwave brain imaging systems. This technique uses microwaves to probe the brain, providing valuable insights into its structure and function. By implementing the FDTD method, we can simulate how microwaves interact with brain tissue, allowing us to develop and refine imaging techniques. This practical application will illustrate how advanced computational methods can address real-world challenges and enhance medical imaging technologies. By the end of this video, you will have a thorough understanding of how to apply electromagnetic computation techniques to solve complex problems, including their practical use in advancing microwave brain imaging systems. In this slide, we delve into the mathematical foundation of electromagnetic problems by exploring Maxwell's equations, which are the bedrock of classical electromagnetism. These equations describe how electric and magnetic fields interact with matter and propagate through space. When Maxwell's equations are expressed in their differential form, they naturally lead to the formulation of various partial differential equations, PDEs, each corresponding to different physical scenarios. Let's start by understanding what PDEs are. PDEs are mathematical equations that involve multiple independent variables and their partial derivatives. They are crucial for describing how physical quantities, such as electromagnetic fields, evolve in space and time. The classification of these PDEs depends on the nature of their second-order derivatives, and they are typically categorized into three types: elliptic, hyperbolic, and parabolic PDEs, each representing distinct physical phenomena. Elliptic PDEs arise in scenarios where the system is in a state of equilibrium, meaning there is no time dependency. For example, the Laplace equation and the Poisson equation, which are derived from Maxwell's equations under static conditions, are elliptic PDEs. These equations describe situations like the electric potential within a region of space due to a static charge distribution. You can see this concept illustrated on the slide, where the distribution of the electric field inside a capacitor is depicted, showing how the field remains constant over time. Hyperbolic PDEs, on the other hand, describe dynamic situations involving wave propagation. The wave equation, which can be derived from Maxwell's equations when considering electromagnetic wave propagation, is a classic hyperbolic PDE. This type of equation is crucial for understanding how electromagnetic waves travel through space at finite speeds, as illustrated on the slide with the schematic of a propagating wave front. Hyperbolic PDEs capture the time-dependent behavior of these waves, making them essential for modeling radiation and signal transmission. By understanding how Maxwell's equations give rise to these different types of PDEs, elliptic for static fields and hyperbolic for wave propagation, we can better choose the appropriate computational methods to solve them. In this video, we will focus particularly on the numerical solution of hyperbolic PDEs because they govern the behavior of electromagnetic waves, as represented by the wave equation derived from Maxwell's equations. As demonstrated in the schematic on the slide, the mathematical model for solving electromagnetic problems, especially in dynamic scenarios, often involves using the finite difference time domain (FDTD) method. FDTD is a powerful numerical technique that allows us to simulate the time domain variation and propagation of electromagnetic fields. However, implementing FDTD requires careful consideration of numerical factors such as boundary conditions and initial values, which are critical to ensuring the accuracy and stability of the simulation. This introduction sets the stage for the deeper exploration of these concepts in the upcoming sections, where we will delve into the specifics of how FDTD can be applied to solve real-world electromagnetic problems, including those in advanced applications like microwave brain imaging systems. In this slide, we introduce the numerical methods used to solve electromagnetic problems, which typically involve partial differential equations, PDEs, governing electromagnetic fields. The process begins by converting these PDEs into linear matrix equations, as illustrated in the schematic on the left side of the slide. This conversion is accomplished using numerical techniques such as the boundary element method, BEM, finite element method, FEM, and finite difference time domain, FDTD, method. Each of these methods involves discretizing the model, in this case, the head model, into a mesh. In the FEM approach, the head model is divided into small volume elements, and the PDEs are reformulated into a weak form that is suitable for numerical computation. This process involves integrating the PDEs over each element to account for variations in the electromagnetic fields, resulting in the creation of local stiffness matrices. These local matrices are then assembled into a global matrix that incorporates boundary conditions and source terms, such as electric currents. Finally, this global matrix equation is solved using numerical linear algebra techniques to determine the electric potential or magnetic vector potential at each node within the mesh. In contrast, the BEM approach discretizes only the surface of the head model into boundary elements. The PDEs are transformed into boundary integral equations, simplifying the problem to a surface-based system. These integral equations are used to create a matrix system that, once solved, yields the potential on the surface of the model. From this surface potential, internal electromagnetic fields can be computed. The schematic shows the meshing process for both BEM and FEM, highlighting the discretization strategy used in each method. The slide also includes a visual representation of the different numerical methods by comparing their performance based on electrical size and material complexity, shown on the right side. In the current state-of-the-art approach for lead field estimation using BEM, the head is described using a few compartments with constant and isotropic electrical conductivity. However, BEM is limited when it comes to handling complex conductivity distributions, particularly those that are anisotropic. On the other hand, FEM and FDTD methods can accommodate arbitrary, anisotropic conductivity distributions. This capability allows these methods to consider thin and highly conductive tissues, such as bone marrow, which are typically neglected when using BEM. FDTD, in particular, is advantageous because it can incorporate arbitrary conductivity distributions and anisotropy without the need for complex meshing techniques required in FEM and BEM. This characteristic makes FDTD especially suitable for electromagnetic brain imaging, as it provides a more accurate and flexible modeling approach. In conclusion, the schematics and illustrations on this slide demonstrate why FDTD stands out as the best option for electromagnetic brain imaging, due to its ability to handle complex material properties and provide detailed insights into electromagnetic field behavior in the brain. In this slide, we delve into the application of the finite difference time domain, FDTD, method for solving electromagnetic problems, with a particular focus on how this method is implemented to simulate wave interactions within a defined computational domain. The diagram before us serves as a visual representation of the FDTD setup, where an incident electromagnetic wave encounters an object, leading to the scattering of waves in various directions. This scenario is crucial in understanding how electromagnetic fields interact with different materials, which is particularly relevant in complex applications like brain imaging. Surrounding the central object in the simulation are perfectly matched layers, PMLs, which are a key feature in FDTD simulations. These layers are strategically placed along the boundaries of the computational domain to absorb outgoing waves, thereby preventing any reflections that could distort the simulation results. The PMLs in the diagram are oriented along the X, Y, and XY directions, ensuring comprehensive absorption of waves from all edges of the grid. This setup allows the FDTD simulation to accurately mimic an open space where waves can freely propagate without artificial boundary effects. The outer boundary of the simulation domain is marked as a perfect electric conductor, PEC, which acts as a reflective surface in some FDTD simulations. In this context, the PEC boundary ensures that no energy escapes the simulation domain except through the PMLs, further enhancing the accuracy of the wave interactions being modeled within the domain. An inset on the right side of the diagram provides a closer look at how the PML functions. The graph in this inset illustrates the gradual increase in conductivity within the PML, which corresponds to a decrease in the electric field as the wave penetrates deeper into the layer. This gradual absorption mechanism is crucial for preventing reflections that would otherwise interfere with the accurate simulation of wave behavior, making the PML an essential component of the FDTD method. In addition, boundary conditions are essential for accurate simulations. Absorbing boundary conditions, ABC implemented to minimize reflections at the edges of the computational domain. Traditional ABCs can introduce errors, leading to the development of perfectly matched layers, PML, by Berenger, 1994. PML absorbs outgoing waves effectively. Uniaxial PML, UPML, introduced by Gedney, 1996, improves computational efficiency, especially for lossy media. Perfectly electric conductor, PEC, and perfectly magnetic conductor, PMC, boundary conditions. PEC conditions set E to 0 on metallic surfaces, while PMC conditions set H to 0 on magnetic surfaces. This slide highlights the numerical approach of the FDTD method, which is crucial for simulating the propagation of electromagnetic waves through complex environments like the human head. We begin by revisiting Maxwell's core equations, which are fundamental to understanding the behavior of electric and magnetic fields. Gauss's law for electricity describes how electric charges generate electric fields. Gauss's law for magnetism asserts that there are no magnetic monopoles and that magnetic field lines are continuous. Faraday's law of induction explains how a time-varying magnetic field induces an electric field, and Ampere's law, with Maxwell's correction, details how a time-varying electric field or an electric current generates a magnetic field. These equations provide the theoretical foundation for our numerical simulation. To discretize Maxwell's curl equations, we use a second-order finite difference approximation within the FDTD method, which involves discretizing both time and space to capture the dynamic behavior of electric and magnetic fields. We employ E's grid, a crucial framework in FDTD, where electric field components E are computed at integer time steps, and magnetic field components H are calculated at half-time steps. This staggered arrangement minimizes phase errors and ensures accuracy. Specifically, X, EY, and EZ are defined at primary grid points, while HX, high, and Hertz are defined at secondary grid points. Each E component is surrounded by 4 adjacent H components, and vice versa. For example, at grid location I+1/2, J, K, the X is influenced by adjacent high and Hertz components. The spatial domain is divided into a grid with increments delta X, delta Y, and delta Z in the X, Y, and Z directions, respectively, while time is divided into increments delta T. We use the leapfrog algorithm, as proposed by Hussein and Seeback, 1996, to iteratively update the electric and magnetic field components based on Maxwell's equations. This algorithm updates fields at alternating time steps with half-step spatial offsets, ensuring a more accurate resolution of the fields within each grid cell by slightly offsetting the phases of field components. To maintain numerical stability, the FDTD method adheres to the Courant-Friedrichs-Lewy (CFL) criterion. The time step delta t must satisfy the CFL condition, which depends on the spatial step sizes delta x, delta y, delta z, and the maximum speed of electromagnetic waves in the medium C max. This criterion ensures the time step is small enough to accurately capture field propagation without introducing numerical instability. It's important to note that reducing the mesh step size by a factor of 2 increases memory requirements by a factor of 8 and computation time by a factor of 16, highlighting the need to balance accuracy with computational resources. Note that accurate gridding is crucial for effective simulation. For uniform and straight geometries, Yee's grid is applied by discretizing them into rectangular cells. However, for non-uniform or curved geometries, this method may introduce errors due to misalignment. For handling non-uniform geometries, 3 approaches are considered. first shifting the geometry, may lead to errors due to misalignment. Second, minimizing cell size, requires more memory and computational power but provides finer resolution. And third, non-uniform cells, staircasing method. This approach approximates curved geometries with staircase cells, offering a flexible transition between boundaries while reducing memory and computational requirements. By utilizing the FDTD method with careful spatial and temporal discretization, boundary condition application, and gridding strategies, we can accurately simulate electromagnetic wave propagation in complex environments such as the human head. This approach ensures that both the electric and magnetic fields are dynamically and realistically modeled, providing valuable insights into their interactions within intricate structures. Finally, to demonstrate the correct implementation of these principles, we simulated wave propagation using a Gaussian waveform as the source. This example, involving ultra-wideband source excitation in the FDTD medium, illustrates the wave propagation through the medium and its absorption at the boundaries. In this slide, we explore the application of the FDTD method for simulating electromagnetic interactions within a human head, as represented by the voxel-based phantom displayed on the right-hand side. The left-hand first image illustrates a perspective view of a human head, discretized into a grid of voxels, which serves as the central object within the FDTD simulation medium. This voxel-based approach allows for highly detailed modeling of the head's complex anatomical structures, providing an accurate representation of how electromagnetic fields propagate through different tissues. The voxel-based phantom ensures that the variations in tissue properties, such as permittivity and conductivity, are accurately captured, allowing the simulation to model how electromagnetic waves scatter and absorb within the different tissues of the head. This is particularly crucial for applications like brain imaging, where precise knowledge of field distribution is essential. As mentioned earlier, the simulation domain is surrounded by PMLs to absorb outgoing waves and prevent reflections that could affect the accuracy of the simulation. The integration of the human head model into this domain allows for a realistic simulation of electromagnetic wave interactions in a controlled environment, where the FDTD method can compute the field's behavior over time. On the right side of the image, the voxel-based phantom image is represented in the FDTD grid form. This high-resolution model is essential for accurately predicting how electromagnetic waves interact with different tissues, contributing to more effective imaging and analysis. In the right side of the slide, the generic form of microwave imaging system is demonstrated, including the array of the antennas surround the head phantom. The combination of the FDTD method with a detailed voxel-based human head phantom provides a powerful tool for simulating and analyzing electromagnetic fields in biomedical applications. This setup allows for precise modeling of wave propagation and interaction within the human head, offering valuable insights for applications such as brain imaging, where understanding the behavior of electromagnetic fields within complex tissue structures is crucial. In general, when an incident electromagnetic wave encounters biological tissue, it is divided into several components: reflection, scattering, absorption, and transmission. The accurate calculation of these components is crucial for simulating and understanding the interactions within biological tissues. Several methods exist to model these interactions based on the tissue's permittivity, permeability, and conductivity. Furthermore, the slide discusses the dielectric properties of tissues in different conditions, such as ischemic and hemorrhagic strokes. The dielectric properties, including permittivity and conductivity, vary significantly between these conditions, influencing how electromagnetic waves interact with the tissues. To ensure the accuracy of the FDTD simulation, the computational domain is surrounded by PMLs, which absorb outgoing waves and prevent reflections that could otherwise distort the results. This allows for a more realistic simulation environment, where electromagnetic interactions can be studied in detail. Additionally, the simulation results of attenuation of the electromagnetic wave in different tissues layer, which includes a comprehensive set of voxels that represent various tissue types, such as skin, fat, bone, gray matter, and white matter, were demonstrated. The voxel model is crucial for developing accurate brain microwave imaging systems for stroke detection, as it provides detailed geometrical information about the human head. At the bottom side of the slide, the dielectric properties of these tissues demonstrated, which are dispersive, meaning they vary with frequency, which is accurately captured using the fourth Kolkol equation in the simulations. This level of detail is essential for designing and implementing the hardware and software components of brain imaging systems, including antenna elements and image reconstruction algorithms. This slide presents the extracted results from an FDTD simulation of a generic microwave imaging system. A key advantage of time-domain solvers like FDTD is their ability to animate the entire process of wave launching, propagation, reflection, and scattering. However, for brevity, only a snapshot of the fields at the 2000th time step is shown. The left side illustrates wave propagation within the phantom model. Here, a portion of the launched wave is seen to have coupled into the brain matter, predominantly traveling along the x-axis through the brain. In addition, the electric field component EZ is plotted as a function of time. Notably, at around the 2400th time step, distortion in the waveforms becomes evident. In this instance, no waveform distortion is observed, however, a slight but noticeable phase shift occurs around the 2000th time step.
The middle column displays the normalized induced currents for different operating frequencies, 1 GHz, 2.5 GHz, and 4 GHz. These results are crucial for understanding the interaction of electromagnetic waves with different tissue types at various frequencies. On the right side of the slide, the specific absorption rate, SAR, distribution is shown. SAR is a critical measure for ensuring the safety of the human body against harmful radiation. Since the proposed antenna is positioned near the head model, calculating and analyzing the SAR is essential. The input power to the antenna is 1 mW, with only one antenna acting as the transmitter at any given time. The SAR must comply with the IEEE public radiation exposure limit of 1.6 W per kilogram. Additionally, the slide presents sample scattering parameters, including reflected loss and transmission loss. These parameters are vital for the inverse scattering algorithm used in brain image reconstruction, which will be discussed in detail in the subsequent playlist on inverse electromagnetic problems. In this playlist, we aim to explore inverse electromagnetic problems and their solutions. These methods will be examined in detail across three categories: quantitative, qualitative, and stochastic, in the next three videos. The overall goal of these methods is to create a model of the environment under test by solving an optimization problem that aligns the measured data in the data space with the system's response in the model space. In this video, we will provide an overview of the inverse electromagnetic problem and explain how these problems are formulated. Then, we will introduce the inverse electromagnetic scattering problem, such as the Born approximation. Following that, we'll demonstrate how to set up and solve the optimization problem using regularization techniques. Finally, we will summarize the different solution methods for addressing this problem. The inverse scattering problem involves estimating the spatial distribution of potential scatterers within an object based on the measured scattered electromagnetic fields. Essentially, an incident electromagnetic field penetrates the object, inducing scattered waves. These scattered waves can be measured in three forms: full wave, transmission, and reflection. This slide shows the illustrations of these three forms, but the measurable quantity is the total field, which is a combination of both the scattered and incident fields. A sample of this total field is shown on the slide. On the right side of the slide, we included diagrams that depict the optimal visualization of the scatterers in different directions and coordinate systems. In illustrating the geometry of a scattering problem, an inhomogeneity is characterized by a distribution of relative permittivity epsilon, x, embedded within another uniform medium with relative permittivity epsilon. An electromagnetic wave is launched from a point with coordinate x, directed towards the inhomogeneity, where it interacts and is scattered to points with coordinates x and x. Close to the scatterer, the wavefronts are non-planar. The geometry of a plane wave propagating in the xy plane is shown, resolving the wave number components in relation to the propagation angle theta. There's also an illustration of a plane wave incident on an extended scattering object composed of various subscatterers. At large distances from the scatterer, the local scattered field components themselves become plane waves. In this slide, we aim to discuss how to derive inverse electromagnetic equations. Let's begin with Maxwell's curl equations, which describe the relationship between the electric and magnetic fields. On the slide, you can see the curl of the electric field R and the magnetic field R for a medium with spatially varying permittivity epsilon R and permeability mu R. These are crucial for understanding how electromagnetic waves propagate through different materials. Next, to derive the wave equation for R, we take the curl of the first equation shown for R and substitute the expression for nabla cross dot R from the second equation. This gives us the wave equation you see, which includes both the electric field R and the induced current source junior. Now, to simplify this and isolate the effects of the material properties, we subtract the corresponding background equation, which assumes the permittivity and permeability are constant, epsilon b and mu b. As shown in the figure, the scattering problem consists of a source G, R, which propagates a wave through a medium with electromagnetic properties ebb and mu b, and in the presence of a non-homogeneous scatter with properties E, R, and mu, R. In this scenario, the following Maxwell equations are valid for any point R of space. The subtraction introduces the concept of the effective current source, junior, which is represented by the expression in the middle of the slide. This current source arises from the contrast between the material's properties and the background. To solve the electric field we express it using Green's function, which allows us to represent the field as an integral over the volume of the medium. You can see the integral form of the solution on the slide. This equation shows how the field at any point depends on the Green's function and the effective current source. The first term on the right side of is the field produced by the impressed source of the problem, which is also called the incident field A, R. The function G, R, R0, is the dyadic Green's function for homogeneous medium, and it is the impulse response, i.e., the solution of the equations for a point source. The second term represents the field due to the displacement or conduction electric currents, while the third term represents the field due to the magnetic polarization charges. If we suppose that there are only non-magnetic materials, i.e., mu equals mu b equals mu 0, then we can rewrite the formula and arrive at the scattering equation, where the total electric field is broken down into the incident field A, R, and the scattered field. The integral involving the contrast function chi, R, which accounts for both the relative permittivity and conductivity differences, gives us the final expression for the total field. In summary, we've walked through the process of deriving the vector wave equation, incorporating the concept of an effective current source, and expressing the solution using Green's functions. This leads to the scattering equation, which is key for understanding how electromagnetic waves interact with complex media. Let's continue with the more complete scenario as set of boundary integral equations. These equations help describe the electric field E1, R, in a volume 5-1 using surface integrals over the boundary S. We express the electric field in terms of the Green's function gr, r, and the surface fields like our and In the first equation, is expressed as an integral over the surface, where the normal vector n interacts with the Green's function and the surface fields. If the point R lies within volume 5-1, this expression gives the electric field but if R lies in volume 5-2, the expression yields 0, as shown. Next, we have a modified form where the Green's function and its derivatives are involved in computing the electric field. This equation is similar but focuses more on the normal components of the surface integrals. Here, the integral also includes contributions from both the electric field and the magnetic field. Moving forward, we apply transposition properties for the Green's function. The curl of the Green's function and the Green's function itself follow specific symmetries, as indicated by the transpose operations. These properties are crucial when solving surface integrals and electromagnetic problems. Now, using these transposition properties, we define two surface current densities, the electric surface current density Js, R, and the magnetic surface current density Ms, R, which involve the normal components of the electric and magnetic fields on the surface. These surface currents represent how the fields behave at the boundary between volumes. In the equation that follows, we express E1, R, in terms of surface integrals involving the Green's function and these surface currents. This form shows how the electric field in V1 depends on the surface integrals, while in V2, the field is 0, as shown by the conditions. Finally, we reach the most general form for the total electric field which is a sum of the incident electric field A, R, and the contribution from the surface integrals involving the Green's function and the surface currents junior. This equation describes the total electric field in terms of both the incident field and the scattered contributions from the boundary. In this slide, we are demonstrating the process of electromagnetic imaging, focusing on both the forward and inverse problems, particularly in brain imaging. Let's start with the forward problem path. The setup begins with the human brain, where we aim to identify anomalies or regions of interest, like the red spot shown in the diagram. The process starts with transmitting signals that interact with the brain. These signals are then directed through a switching matrix, which controls and routes the signals to a vector network analyzer, VNA. The VNA collects the data and produces a scattering matrix, which reflects how electromagnetic waves scatter when they encounter different tissues in the brain. This scattering matrix is essential for understanding the interaction of fields with the brain's internal structures. The data is then sent to the processing unit, which processes the scattering information, and the output is a quantitative image of the brain, helping to locate the region of interest. Mathematically, this forward problem is modeled using Maxwell's equations. We describe the relationship between the electric field E, the magnetic field H, and the current sources J and M through these differential equations. These equations consider the effects of the material properties, such as permittivity epsilon, permeability mu, and conductivity sigma, as well as how the electromagnetic fields are propagated and interact with different regions of the brain. Next, let's move to the inverse problem path. In this part, the goal is to reconstruct the internal electromagnetic properties of the brain based on the scattering data collected earlier. The key equation used here expresses the electric field at any point r as a sum of the incident electric field A, r, and a term involving an integral over the surface. This integral term captures how the scattered fields contribute to the total field based on the Green's function and current distribution. The output of this inverse problem is the retrieval of the effective current distributions J and M, which are crucial for generating the final quantitative image of the brain, helping visualize anomalies. In summary, the forward path models the scattering of electromagnetic waves through the brain, while the inverse path reconstructs the internal properties using the collected scattering data, ultimately resulting in a detailed image of the brain for diagnostic purposes. This slide illustrates the different solution methodology of inverse scattering problem. In the realm of electromagnetic imaging, the methods for producing images can be broadly categorized into quantitative, qualitative, and artificial intelligence imaging approaches. Each method provides different insights based on the processing of the scattering matrix, which is generated by analyzing the interaction of electromagnetic waves with the object. As shown in the slide, each of these have their respective subtypes, which are crucial in different applications depending on the type of information one seeks to extract from the data. First, let's explore quantitative imaging. This method focuses on generating precise, measurable information about the internal properties of an object. Quantitative imaging often deals with the reconstruction of physical parameters such as permittivity, conductivity, or dielectric constants of the materials inside the object. The scattering matrix, once processed, gives us detailed images that allow for accurate identification of the material's electrical properties. In the slide, we see an example where the imaging highlights a brain with a red dot, representing an abnormality like a tumor. The image provides detailed information about the distribution of electromagnetic properties, which are essential in medical diagnostics and material characterization. On the other hand, qualitative imaging focuses more on visualizing the structure or shape without providing precise numerical values. It is used to differentiate between regions of interest based on contrast but not the specific material properties. For instance, the slide shows an image with different geometric shapes, signifying the ability of qualitative imaging to differentiate between boundaries and structures within the object, but without the fine details of the material's electromagnetic parameters. It's often applied in cases where detailed measurements are less important than simply identifying the presence or absence of certain features. Lastly, machine learning is becoming an integral part of modern imaging. By processing large sets of scattering data, machine learning algorithms learn to predict or enhance images based on previously observed patterns. This technique can improve the accuracy of both quantitative and qualitative imaging by refining the images, identifying hidden patterns, or predicting missing information. Machine learning can aid in situations where traditional methods struggle to produce clear or high-resolution results. In summary, the slide differentiates between the precise, measurement-oriented approach of quantitative imaging and the broader, more structural focus of qualitative imaging. Both approaches benefit from machine learning, which enhances imaging by predicting patterns and improving image clarity based on large datasets. These methods, when combined, provide a powerful set of tools for diagnosing, analyzing, and interpreting electromagnetic imaging data. In summary, while quantitative imaging offers detailed, measurable insights into material properties, qualitative imaging provides a structural or shape-based understanding of the object. Machine learning further enhances these methods, providing tools for better image reconstruction and analysis. Each technique, whether it's Gauss-Newton or LSM, plays a critical role in addressing specific challenges in electromagnetic imaging, depending on whether one seeks detailed numerical properties or simply the shape and presence of objects. After introducing the inverse electromagnetic problem, we will now shift our focus to quantitative imaging solution. Quantitative imaging methods aim to reconstruct numerical values representing the physical properties of the object being studied. These values provide measurable, accurate information that is often required for medical diagnostics or materials science applications. Here we are going to explain one of the main methods under quantitative imaging, which is called Born Iterative Method, BIM. BIM is typically used when the scattered field is weak and assumes that the object's internal contrasts are small. This iterative approach starts from an initial guess and updates the solution step by step, refining the reconstruction. To describe the BIM solution, here we brought the brain electromagnetic imaging example. Electromagnetic brain imaging devices use multiple antennas to transmit and receive high-frequency electromagnetic waves into the brain, which interact with brain tissues, and the scattered field will be received in antenna. These interactions cause scattering due to differences in the tissue's electromagnetic properties. In scattering theory, the problem is described by the Lippmann-Schwinger integral equation, which relates the total field to the incident and scattered fields. The scattered field is expressed as the integral of the source, Green's function, and contrast function, which forms our forward model. To solve this problem, we employ an iterative method that utilizes the Born approximation at each step. During the kth iteration of this method, the total field k-1 is computed for the contrast function k-1 obtained in the previous iteration, using the state equation. By substituting k-1 into the data equation and applying the Tikhonov regularization method, the optimization problem is solved to obtain k. For the first iteration, k0 is chosen arbitrarily. The slide presents the formulation associated with this solution, including the closed-form solution. In right side, we brought the schematic of the iterative method based on initial assumption in fine model and updating coarse model. First, we define an initial model as a guess and solve the forward problem, which involves simulating scattering parameters using FDTD computational method based on assumed point scatter sources, permittivity and conductivity. Then, we define the inverse problem, which involves adjusting the scatter parameters to minimize the difference between the simulated and actual scattering parameters. To reduce this error, we must solve the optimization problem. By using BIM and Tikhonov regularization, we refine the scatter estimates. This slide focuses on qualitative imaging methods, which are vital for understanding anomalies, boundaries, and other key qualitative features within tissues, especially in medical diagnostics like brain imaging. Instead of providing precise material properties, qualitative approaches identify areas of interest based on differences in dielectric properties. The confocal imaging process, depicted on the left, forms the backbone of these methods. This approach simplifies solving the inverse scattering problem by treating each scatterer, such as a tumor or stroke, as an electromagnetic point source. The delay and sum beamforming technique, shown in the flowchart, ensures that signals received from scatterers are time-shifted and aligned for coherent summation, leading to a focused energy map. The formula illustrates how the distance, τn, between the antenna and target is calculated to apply the proper time shift for signal alignment. In the signal processing stage, the backscattered signals are analyzed to compute the energy at each pixel, revealing anomalies based on variations in dielectric constant. The image formation at the bottom left visualizes this energy distribution, aiding in the detection of abnormalities. On the right side of the slide, the equiangular and equidistant scanning system is introduced, where an array of antennas sends and receives signals in equal angular intervals, denoted by def. This configuration ensures uniform coverage of the tissue and simplifies the cancellation of background reflections. The diagram in the middle shows the effective permittivity plot, where the permittivity varies with angular position due to thicker muscle layers on the sides of the head. These permittivity values are computed from the reflected signals and provide insights into the tissue's composition. At the bottom right, we see how delay and sum beamforming is applied in practice. When the beamformer is steered towards the correct location of the scatterer, denoted by R equals R0, coherent summation occurs, resulting in a stronger signal. If misaligned, incoherent summation leads to a weaker response. The combination of delay and sum processing with equiangular scanning enhances image clarity, allowing for precise identification of anomalies based on dielectric property differences. In this slide, we explore machine learning, ML, and deep learning solutions for addressing the inverse electromagnetic, scattering problem, which involves retrieving the permittivity of dielectric scatterers from measured scattering data. This problem involves determining the permittivity epsilon of dielectric scatterers from the measured scattering data S. The scattering model G, which is typically nonlinear due to the multiple scattering interactions, making traditional iterative approaches computationally expensive and time-consuming. To tackle this, the slide introduces convolutional neural networks, CNNs, as an efficient alternative for solving full-wave inverse scattering problems. CNNs learn a mapping epsilon hat equals GS where epsilon hat is the predicted permittivity from the scattering data S. CNNs are well suited to handle the spatial complexities of M scattering, bypassing some of the challenges associated with conventional iterative techniques and provide real-time solutions. This approach is particularly promising for achieving real-time imaging solutions. In more details point of view, the CNN combination with U-net architecture can be divided to different training schemes for solving inverse scattering problems. One of them is direct inversion. This scheme uses CNN to directly map scattering data to the permittivity distribution without integrating additional physics constraints or models. 2. Backpropagation. A more conventional approach where the neural network learns through optimization using backpropagation. In this scheme, CNN training is performed using backpropagation with physics-informed loss functions, which may include Tikhonov regularization, improving the inversion process by penalizing unrealistic solutions. 3. Dominant current scheme, DCS. DCS emphasizes the dominant current contributions in the inversion process. The dominant current ID can be obtained by singular value decomposition, SVD, of the forward model matrix G. This approach allows for faster and more accurate computations. In addition, a key aspect of the artificial intelligence-based approach is how physics is incorporated into the ML models. 3 strategies are highlighted as shown in the right side of the slide. 1. Learning after physics processing. In this approach, physics-based models are used to pre-process the input data for ML models, ensuring that the data passed to the neural network is physically meaningful, which can guide the model toward more accurate solutions. Here, the data preprocessing involves applying a physics-based model to obtain an initial estimate of epsilon. This preprocessing helps to set a physically meaningful input for the ML model. 2. Learning with physics loss. Here, physics knowledge is embedded directly into the loss function of the neural network. This might involve adding regularization terms or physical constraints, such as Tikhonov regularization, to guide the network in producing physically consistent solutions. The Tikhonov regularization technique plays a vital role in stabilizing the inversion process by adding a penalty for overly complex solutions, thus ensuring the smoothness of the reconstructed permittivity profile. This regularization is crucial for mitigating the ill-posed nature of inverse problems and preventing overfitting, especially when dealing with noisy or incomplete data. 3. Learning with physics models. The final approach uses physics-based insights to shape the architecture of the ML model itself, ensuring that the network structure respects known physical laws and relationships, which improves the model's ability to generalize and produce meaningful predictions. For instance, the network might be designed to inherently respect conservation laws or other physical principles, optimizing the structure to align with these constraints. Combining deep learning with physics-informed ML methods offers a promising approach to inverse M problems. This integration facilitates rapid and accurate solutions, significantly reducing computation times compared to traditional methods. The potential applications are extensive, including medical diagnostics, geophysical exploration, and non-destructive testing, where real-time quantitative imaging is crucial. The synergy between advanced deep learning techniques and physics-based insights represents a major step forward in addressing the computational challenges associated with conventional iterative algorithms.
Welcome to our presentation on quantitative electromagnetic imaging. This field focuses on reconstructing the internal properties of objects, like the human brain, by analyzing how electromagnetic waves scatter upon interaction with these objects. In particular, we will explore microwave tomography, a technique used in medical imaging to detect anomalies such as strokes and tumors, by analyzing microwave scattering patterns. The process involves solving an inverse problem, where the challenge is to determine internal material properties, such as permittivity and conductivity, from measurements of scattered electromagnetic fields. We will cover both the forward problem, how electromagnetic waves scatter given known object properties, and the inverse problem, how we reconstruct these properties from scattered field measurements. To simplify our approach, we use techniques like linear approximations and, for more complex cases, nonlinear inversion. We'll also investigate advanced algorithms and emerging methods like machine learning that enhance imaging accuracy and speed. Let's delve into how these principles apply to microwave brain imaging and the future directions of this exciting field. For starting the quantitative imaging of electromagnetic wave scattering problems, we put here a visual illustration. Let's go over the key elements presented. We start with the wave equation, which governs how waves propagate, whether they are electromagnetic wave equations. In the context of scattering problems, this equation helps us understand how waves interact with objects, known as scatterers, that are in their path. Next, we have the Green's function, which is a fundamental solution to the wave equation. It tells us how a point source at one location affects the wave field at other locations, as shown in the right side of the slide. This function becomes especially important when solving wave equations in inhomogeneous media, where perturbations, such as scatterers, alter the wave's behavior. Once the Green's function is applied, the wave equation can be transformed into an integral form. This captures how the wave interacts with the scatterer by integrating the scatterer's influence over a region of space. The Born series expands on this by expressing the scattered field as a series. The first-order Born approximation, which is the simplest and most used solution, assumes that the scatterer's effect on the wave is weak enough to ignore higher-order interactions. This makes it a linear approximation of the scattered field and simplifies the overall problem. In the left side, we see an incident plane wave that interacts with a scattering source. The scatterer produces a scattered spherical wave, which is phase-shifted relative to the original incident wave. This phase shift is a key characteristic of wave scattering. This approximation is particularly useful for low-contrast or weak scatterers, where the scatterer's influence on the wave field is minimal, making the Born approximation both accurate and computationally efficient. By assuming weak scattering effects, the Born approximation reduces the intricate interactions between waves and scatterers into a manageable, linear solution. This approach is particularly useful in practical applications, such as medical imaging. In this slide, we are looking at the mathematical formulation of the electromagnetic scattering problem and the application of Tikhonov regularization methods for solving inverse electromagnetic scattering problems. We start with the total electric field equation. This equation represents the sum of the incident field and the scattered contributions due to the interaction with the scatterer. The Green's function, GB, R, describes how the wave propagates through the background medium, while the contrast function chi, R, characterizes the properties of the scatterer. We then have a second expression for the total field, which differs slightly by using a domain-specific Green's function, GD, R, tailored for the particular medium of interest. Finally, we introduce the scattered field equation. This equation relates the scattered field to the total field and the Green's function GS, R, which represents how the wave interacts with the scatterer. Now, let's move to Tikhonov regularization. This technique is crucial when dealing with inverse problems, especially when data is noisy or incomplete. The goal is to minimize the residual between the predicted model, X, and the observed data, B, while adding a regularization term, controlled by a parameter lambda, to prevent overfitting. The solution to the classical Tikhonov regularization problem is given by a simple matrix formula involving the Hermitian transpose of matrix A. Next, we generalize this method by introducing a matrix L that adds more flexibility in controlling the regularization. This is particularly useful in cases where additional constraints or properties of the solution are needed. In conclusion, these mathematical tools help us model and solve the complex interactions of electromagnetic waves with scatterers and deal with the inherent instability of inverse problems using regularization techniques. In the left side of the slide, we briefly discuss two important iterative methods used in electromagnetic imaging, the Born iterative method and the distorted Born iterative method, DBIM. BIM uses the Born approximation at each iteration. At the kth step, the total field etot k1, R, is computed based on the contrast function from the previous iteration, gk1, R. This total field is then used in the data equation to solve the inverse problem and update the contrast function to chi k, r, backslash. The process starts with an arbitrary initial guess for backslash chi underscore 0, r, backslash. Tikhonov regularization is often used to solve the matrix form of the optimization problem that arises at each step. On the other hand, dBIM on follows a similar approach to BIM but updates the background medium's Green's function at each iteration. The method reconstructs the difference between the current and previous contrast functions, delta chi k1 equals chi k1. The data equation here includes terms for the scattered fields caused by both chi k1, r, and delta chi k1, with the background medium being related to chi k1, r. Tikhonov regularization is again used to solve the optimization problem at each iteration. Both methods iteratively refine the contrast function to improve the reconstruction of the object's internal properties, providing more accurate imaging results over time. In this slide, we explore the process of solving the inverse scattering problem in microwave brain imaging through forward and inverse modeling techniques. These methods are crucial for translating electromagnetic data into accurate reconstructions of brain tissue properties. The inverse scattering problem is both nonlinear and ill-posed, meaning it can have multiple solutions or solutions that are highly sensitive to noise and perturbations in the data. This complexity makes achieving stable and accurate reconstructions challenging. The figure in the top left corner of the slide illustrates how the inversion process bridges the image space, representing brain tissue properties, and the data space, the measured electromagnetic fields. It highlights how the goal of inversion is to reconstruct an accurate image from the data, managing noise, and ensuring accuracy through regularization techniques. To address the ill-posed nature of the problem, incorporating prior information is essential. This includes known tissue properties or anatomical constraints, which help to constrain the solution space and improve stability. The object space versus image space diagram, bottom left, demonstrates this concept. It shows the transition from object space, the actual physical properties of brain tissues, to image space, the reconstructed image. This diagram emphasizes how prior knowledge about tissue properties guides the inversion process, ensuring that the final image accurately reflects the brain's internal structure and minimizes errors. The surrogate model solution, as depicted in the flowchart on the right side of the slide, provides a detailed view of the iterative process involved in forward and inverse modeling. The process begins with a coarse model as an initial guess, which serves as a baseline simulation of electromagnetic fields based on preliminary estimates of brain tissue properties. Iterative tomography is used to refine this coarse model. This involves solving the forward problem, e.g., using finite difference time domain, or FDTD, to simulate scattering parameters and comparing these simulations with actual measurements. Each iteration updates the model to improve accuracy. It starts with an epsilon perturbation, which represents changes in the medium's properties, such as permittivity. This perturbation causes the incident wave to scatter, producing a scattered field. Regularization techniques are crucial throughout this iterative process. They stabilize the solution and guide it towards biologically plausible results, addressing the ill-posed nature of the problem and reducing sensitivity to noise. Tikhonov regularization shows how priori knowledge and penalty terms are applied to ensure solution smoothness. The right side shows the iterative approach, emphasizing the importance of stopping once a stable solution is achieved. After several iterations, the coarse model is refined into a fine model, providing a detailed and accurate reconstruction of the brain's internal structure by solving the forward problem at a higher resolution and comparing updated simulations with measured data. This technique refines the solution over successive iterations. Rather than adding a fixed penalty, the solution is progressively improved with each iteration. The stopping rule is essential here, as it prevents overfitting, stopping the process when the solution stabilizes. In microwave brain imaging, this helps fine-tune the model, enhancing the clarity and accuracy of the image. This slide offers a comprehensive overview of how forward and inverse modeling techniques address the inverse electromagnetic scattering problem in quantitative microwave brain imaging. By integrating prior information, employing iterative refinement, and applying regularization, the accurate and biologically relevant reconstructions from electromagnetic data can be achieved. In the next slides, we will introduce the detailed walkthrough to provide a comprehensive view of the surrogate models process in microwave brain imaging. Each step, from importing the brain phantom to solving the inverse problem, is crucial for accurately reconstructing the brain's electromagnetic properties. In the first step of the surrogate model, we need the measured signal, which can be obtained the microwave imaging system or can be done by simulating the full system. Here we proposed the totally in silico system. For this we begin by importing a brain phantom into the computational medium. The phantom serves as the true representation of brain tissue properties, which is essential for simulating scattered electromagnetic fields. The measurements are based on this scattered field, which are recorded using external sensors. This scattered field is created by illuminating the brain with microwave signals, and it is the basis for further processing in the model. The function getScatteredField computes the scattered field for a given image contrast map. The main inputs to this function include the contrast map, which defines the spatial distribution of electrical properties in the brain, and the incident field, microwave signal. It calculates the scattered field ES, which represents the difference between the total electric field and the incident field. The function solves the scattering equation using the finite difference time domain (FDTD) method on a coarse grid. The grid's mesh geometry is defined by the medium dimensions, sensor positions, and the wavelength of the microwaves, ensuring that the grid size is sufficiently fine to capture significant scattering. The domain is discretized into a grid mesh, where each grid cell corresponds to a region of the brain with constant electromagnetic properties. The mesh resolution is defined by spatial discretization, typically in millimeters, depending on the size of the brain and the wavelength of the microwaves, 1-3 GHz. Each grid point is assigned a permittivity and conductivity value. For example, brain tissue, bone, and cerebrospinal fluid have different permittivity values. The contrast map consists of relative permittivity and conductivity, representing the brain's tissue properties. The function returns the scattered field measurements as ES, which will later be compared with simulated fields from the model. These fields are then stored for future comparison in the inverse problem. In the scenario, the scattered field is modeled using the electromagnetic wave equation, solved using finite difference time domain (FDTD) techniques. Here, ES is the scattered field, GS is the Green's function, ET is the total electric field, and tau is the contrast function, which accounts for variations in the medium's properties. Once we have the scattered field measurements, the next step is to extract the basic boundaries from the medium. This step leverages prior knowledge of the brain's anatomy and the sensor positions to generate an initial guess of the internal structure. This prior knowledge is essential because the inverse scattering problem is ill-posed, meaning multiple solutions could explain the same data. The coarse model is essential to reduce the problem's complexity in the early stages of the iteration. This model has a lower resolution and approximates the real object with larger mesh elements, speeding up the forward problem's solution. By imposing these constraints, we guide the solution towards biologically plausible configurations. The initial guess of the brain structure is represented by the coarse model, which simplifies the problem. This model discretizes the brain into large, low-resolution grid elements. The relative permittivity and conductivity values are assigned based on prior knowledge of tissue properties. The coarse model represents the discretized form of the permittivity distribution. The coarse model is initialized in the getincident field function, where we allocate the grid size I times j, which corresponds to the number of pixels in the discretized medium. In this phase, the mesh elements are much larger compared to the fine model. This results in a low-resolution approximation of the brain's structure. The typical grid spacing might be 5 to 10 millimeters, simplifying the solution space for the inverse problem. Prior anatomical knowledge from MRI or CT scans is used to place boundary conditions, such as the outer skull and major tissue layers, within the mesh. The getincident field function defines how the initial microwaves propagate through the medium, which represents the medium before any scattering occurs. The function outputs the incident field EI, used as the basis for forward modeling in later steps. After generating the coarse model and obtaining the initial incident field, we map this information to a fine model. The fine model is a higher resolution version of the coarse model, containing many more grid points and thus providing a more detailed view of the brain structure, which enables a more accurate forward simulation and inverse solution. The fine model is created by interpolating the coarse model and updating it with information obtained from prior iterations. This transformation is crucial because while the coarse model helps reduce computational complexity in early iterations, the fine model allows for a more accurate and refined solution as we approach the final stages of the problem. The fine model captures detailed variations in tissue properties and is used for more accurate forward simulations. Interpolation and refinement step is crucial because it transforms the low-resolution grid into a higher-resolution mesh. The coarse model's electrical properties, permittivity, conductivity, are interpolated to fit the fine model's grid and is updated iteratively with each step. The mapping from coarse to fine is not a separate function but is an iterative process. Each iteration updates the model using the difference between simulated and measured fields, effectively refining the solution. The FDTD2D function is then used on this fine model to compute the forward solution. With the fine model in place, we now simulate the scattered fields by solving the forward problem using finite difference time domain (FDTD) methods. FDTD numerically solves Maxwell's equations for the electric and magnetic fields across the fine model grid, producing simulated scattering data. FDTD calculates the time-dependent evolution of electric and magnetic fields at every point in the fine grid. It applies Yi's grid for discretizing Maxwell's equations and computes the scattered field by subtracting the total field from the incident field. The FDTD function performs the forward simulation using the FDTD method, solving for the electromagnetic fields across the fine grid. Its inputs are the fine model's electrical properties, permittivity, conductivity, and the incident field. The output is the scattered electric fields at the sensor locations. The fine model's grid consists of small cells, where each cell corresponds to a specific value of permittivity and conductivity. FDTD uses this mesh to update the electric field at each time step. The permittivity and conductivity values from the fine model are used to solve Maxwell's curl equations, describing the evolution of the electric field in the medium. The simulated scattered fields are then compared with the actual measurements obtained in the first step. The difference between the two, i.e., the residual field, helps guide the next update of the model. This process is repeated iteratively to gradually refine the solution. The residual field is computed by subtracting the simulated scattered fields from the measured ones. The FDTD forward solution is implemented in the FDTD2D function, which calculates the electric fields and stores the results for comparison. The iterative refinement is based on minimizing the difference between ES measurement and ES simulated. Finally, in the fifth step, we solve the inverse problem to update the coarse model parameters based on the differences between simulated and measured scattered fields. This step is critical because the problem is inherently ill-posed and requires regularization techniques to ensure a stable and biologically plausible solution. One common technique used is Born approximation, which linearizes the relationship between the scattered field and the contrast function tau. The contrast function is updated iteratively to improve the match between simulation and measurement based on reducing the residual field. Regularization, such as Tikhonov regularization, is also applied to stabilize the solution and avoid overfitting and reduce sensitivity to noise, ensuring the model remains smooth and biologically plausible. The inverse problem aims to minimize the cost function, which is demonstrated in the slide. Where epsilon is the permittivity, alpha is the regularization parameter, and the second term enforces smoothness in the solution. This penalty term alpha is added to the cost function to ensure the smoothness of the solution. The Born approximation updates the contrast function tau as tau n plus 1 equals tau n beta delta es. The inverse solution is implemented iteratively, with updates to the contrast map, permittivity, and conductivity, based on the residuals. Regularization ensures that the updates are smooth and stable. This is reflected in the getScatteredField function and related inverse solvers. In this final step, the goal is to iteratively update the course model by solving the inverse problem. The inverse problem uses the difference between the simulated and measured scattered fields to refine the initial guess. This update is performed iteratively until the simulated fields closely match the measurements. In this slide, we will explore the formulation, application, and computation of the dyadic green function, particularly in the context of 2D electromagnetic problems in a homogeneous medium. We begin with the mathematical definition of the dyadic green function for a homogeneous medium, denoted GD. This function is crucial for solving wave propagation problems and is expressed using the Hankel function of the second kind, which models how waves radiate in cylindrical coordinates in 2 dimensions. Kb represents the wave number of the background medium. The green formula is essential for determining how electromagnetic waves propagate from a source point or to an observation point or in 2D space. Moving on to the diagram in the center, we see a visual representation of a scattering problem. Region E1 and Region E2, shown in green and pink respectively, represent 2 different materials or domains, each characterized by their dielectric constants epsilon1 and epsilon2. Surrounding them is a background medium with dielectric constant epsilon(b). Within this setup, we are particularly interested in the dyadic green function, denoted GD, which describes the wave propagation within the domain D. This domain could represent a scatterer, an object that interacts with the incident field. Additionally, the scattered field, labeled GS, is the portion of the electromagnetic wave that interacts with and reflects off the scatterer. This interaction is governed by the Lippmann-Schwinger equation, which is central to solving scattering problems by relating the total field as the sum of the incident and scattered fields using the green function. The next section of the slide focuses on 2 key methods for computing the green function in different domains. The first method, labeled getGreenFunction(S), computes the green function for a measurement domain. This method takes in a model that contains both the measurement points, denoted R, and the pixel coordinates, x, y, of the domain. The green function is calculated for the measurement points relative to the pixels in the domain. The output is in the form of a 3D matrix with dimensions m times n times f, where m is the number of measurements, n is the number of pixels, and f represents the number of frequencies at which the green function is computed. The second method, getGreenFunction(D), computes the green function for an image domain. In this case, the function takes a model and an array of indexes that represent reference points in the image. It computes the green function for selected pixels in the image relative to the reference points. The output is also a 3D matrix, but with dimensions p times n times f, where p is the number of reference points, n is the number of pixels, and f is the number of frequencies. Now, let's discuss Green's function for specific cases, such brain imaging. The equations provided describe the Green's function for 2 important conditions. First, for the case where R not zero, i.e., when the source and observation points are distinct. Which J1 is the first-order Bessel function of the first kind, while H0, 2, is the Hankel function of the second kind, which captures the wave propagation behavior in this scenario. This equation describes how waves propagate from a source to a point at a distance or from the source. In the second case, when R equals 0, i.e., when the source and observation points coincide. In this related equation, H1, 2, is the first-order Hankel function of the second kind. This expression gives us the behavior of the Green's function at the source point itself, where the observation and source points are identical. Finally, at the bottom right of the slide, we have 2 3D plots representing the real and imaginary parts of the Green's function. The plot on the left illustrates the real part, which shows a peak at the source and concentric wave-like oscillations radiating outward. This visualization captures how the Green's function behaves spatially in real terms as the wave propagates. The plot on the right shows the imaginary part of the Green function. This part emphasizes the dissipative or absorptive aspects of the wave as it propagates through the medium. Both visualizations provide insight into the wave dynamics in 2D space, showcasing how the green's function represents the complex interaction of electromagnetic waves in this context. This slide introduces us to two common source waveforms, Gaussian and cosine modulated Gaussian, and demonstrates their importance in wave simulations. We also will look at the coarse models of permittivity and conductivity, which are crucial for accurate simulation of wave propagation through heterogeneous materials. First, we focus on source waveforms' initialization and their respective impact on the simulation model. We'll explore two primary types of waveforms and how they are used, followed by a look at the corresponding permittivity and conductivity models. We begin with the Gaussian waveform. This equation represents a simple Gaussian pulse, where t0 is the time at which the pulse reaches its peak, and tau defines the width of the pulse. The waveform rapidly grows to a peak and then symmetrically decays, forming a smooth bell-like curve, as we can see in the top right plot. This plot shows the Gaussian waveform at a frequency of 3 GHz, peaking at around 4 nanoseconds. The amplitude rises smoothly and then falls back to zero, demonstrating the typical behavior of a Gaussian waveform. The second type of waveform is the cosine modulated Gaussian waveform. This is essentially a Gaussian waveform modulated by a cosine function. The cosine term introduces oscillations, which modulate the Gaussian envelope. This can be seen in the bottom right plot, which also shows a waveform at 3 GHz. Unlike the pure Gaussian waveform, the cosine modulated version oscillates about zero, showing a more complex structure with alternating positive and negative amplitudes. These oscillations gradually fade out as the envelope decays, forming the typical behavior of a modulated Gaussian pulse. Finally, at the bottom of the slide, we see two visualizations showing the coarse model of permittivity, left, and conductivity, right. These images are typically representations of the medium through which the electromagnetic waves are propagating. The coarse model permittivity plot represents how the permittivity varies across the domain. Permittivity, which influences how the medium interacts with the electric field, varies spatially within the model. The visualization uses color to show different permittivity values, with the central region likely representing an object or material of interest, such as biological tissue. The coarse model conductivity plot shows how the electrical conductivity varies across the same domain. Conductivity impacts how much of the electromagnetic wave is absorbed by the medium, with higher conductivity regions absorbing more energy. Like the permittivity model, this plot also shows variation across the domain, with higher conductivity values shown in brighter colors. Both models are essential for understanding the interaction between electromagnetic waves and the medium, as they help simulate realistic physical behavior. The color scales in these plots help identify regions of different permittivity and conductivity, which could represent different materials or tissues in an imaging or wave propagation problem. This slide provides a comprehensive view of wave propagation, illustrating how electromagnetic fields evolve over time in both low and high permittivity environments. The incident and scattered fields help us understand how waves interact with objects in the medium, while the final images on the right offer a potential reconstruction of the medium's internal structure, showing how different permittivity levels affect wave interaction and imaging results. In the last slide, we will explore wave propagation and the behavior of the incident and scattered fields at different time steps. This analysis gives us a clear understanding of how electromagnetic waves interact with different media over time, particularly within a heterogeneous environment. We begin by looking at the plots on the top left, which show the incident and scattered fields at various time steps. Each column represents a different moment in time during the simulation, starting with time step 0, progressing to time step 50, and finally time step 99. In the first row, we see the incident field at each of these time steps. 1. At time step 0, the incident field is just starting to propagate, with very little change across the medium. 2. By time step 50, the field has propagated further, but it still exhibits a nearly uniform pattern, suggesting minimal interaction with objects in the medium. 3. By time step 99, the field has propagated even more, showing subtle variations as it moves across the domain. The color scale in these plots indicates the field's amplitude at each point, with blue indicating negative values and red indicating positive values. These amplitudes change as the wave propagates, reflecting the oscillatory nature of the wave. Moving to the second row, we observe the scattered field at the same 3 time steps. 1. At time step 0, there is minimal scattering, as the wave has just started to interact with the medium. 2. By time step 50, the scattered field becomes more pronounced, with a pattern emerging where the wave interacts with the material inside the medium. 3. By time step 99, the scattered field is well developed, with noticeable variations that correspond to the structure of the object within the medium. The scattered field indicates how much of the incident wave is being reflected, absorbed, or redirected due to interactions with objects in the medium. The development of the scattered field over time provides insight into the internal structure of the object. At the bottom left, we shift focus to wave propagation in 2 different material conditions. These plots represent wave propagation for low and high permittivity values, allowing us to compare how the material properties of the medium affect wave behavior. In the low permittivity case, the wavefront is smoother, and the propagation shows fewer internal reflections or interactions. In contrast, in the high permittivity case, there is more interaction between the wave and the medium, with noticeable internal reflections and scattering patterns. The wavefront is more disturbed, and the field exhibits stronger variations due to the increased dielectric constant. Both cases are crucial for understanding how waves behave in different materials, with the permittivity directly influencing how fast the wave travels and how much it interacts with the medium. Finally, on the right side of the slide, we observe 4 grayscale images, a D, that appear to represent reconstructed or modeled images of the medium. These images are the results of an imaging or reconstruction process using the scattered field data from earlier. Images show a more defined structure, possibly indicating a region of high permittivity or strong interaction. Images B, C, and D progressively show fewer clear boundaries, which could indicate changes in the material properties or imaging resolution. The grayscale bar beneath the images represents the scale of the data values, such as permittivity, conductivity, or wave interaction strength, with darker colors corresponding to higher values and lighter colors to lower values. These images could be used to map the internal structure of an object, such as in medical imaging or material analysis. This video focuses on qualitative imaging methods, which are vital for understanding anomalies, boundaries, and other key qualitative features within tissues, especially in medical diagnostics like brain imaging. Instead of providing precise material properties, qualitative approaches identify areas of interest based on differences in dielectric properties. The confocal imaging process, depicted on the left, forms the backbone of these methods. This approach simplifies solving the inverse scattering problem by treating each scatterer, such as a tumor or stroke, as an electromagnetic point source. Regarding the multistatic and near-field imaging characteristics of the imaging setup, to reconstruct an image we need to apply a focused beamforming algorithm such as confocal beamforming algorithm. For this, the first step is identifying focal points to calculate energy pattern of the reflected signal at these points, which for multistatic imaging algorithm, will be done by coherence signal integration. Radar-based imaging techniques need prior information about the effective permittivity value of the medium. This value is usually set based on the average permittivity of tissues at midpoint frequency. However, in clinical application, the average effective permittivity may be variant in different individuals who have different body shapes and habitus. Hence, effective permittivity estimation technique is usually needed to estimate the overall effective permittivity of the medium prior to imaging. This slide explains a microwave imaging system designed to analyze and reconstruct images of internal structures, such as biological tissues. The diagram on the top left shows the microwave imaging system overview, including an antenna array surrounding a tissue sample, likely biological. The antennas emit microwave signals, which pass through the tissue and are scattered. The tissue under investigation scatters the microwaves, creating an electromagnetic response. The scattered microwave signals are collected by the antennas and fed into microwave electronics for processing. The switching interface selects the active antennas at each moment, and data is transferred to a computer for further analysis. This setup represents the real-world implementation of microwave imaging, where signals interact with tissue to provide information about its internal structure. In addition, at the bottom, the equivalent electromagnetic source model of the system is demonstrated, which is the basic assumption of the qualitative imaging system. The figure represents wave propagation from the source to the tissue, back to the receiver. The blue dashed lines represent the wave interaction with internal structures, which scatter the signal. The scattered fields are used to backproject an image of the tissue's internal structure. This process iteratively reconstructs an image by combining data from multiple antennas. Signals from multiple sources are represented as time-domain waveforms. These signals correspond to the scattered field measured by different antennas. The signals are time-shifted and summed. This time-shifting process adjusts the signals to align with the delay caused by the signal's interaction with different parts of the tissue. Once aligned, the signals are summed and processed to extract useful features from the measurements. Finally, the processed signals are used to form an image, showing the internal structure of the tissue, with color-coded intensities that represent different tissue properties, e.g., permittivity, conductivity. Time delay formula, tau-n, calculates the time delay based on the distance from the source, transmitting antenna, to the scattering point in the tissue and back to the receiving antenna. The time delay helps align the signals for proper image reconstruction. Signal correction equation, SIN, represents the signal processing step where the average value is subtracted from the signal to remove noise or unwanted artifacts. As shown, the signals from each antenna are processed to extract useful information, such as intensity and phase, and these are combined to generate a final image. This process helps visualize the internal permittivity and conductivity properties of the tissue. Image intensity formula, IN, represents the intensity of the reconstructed image. It sums over all antennas after accounting for the time delay, producing the final image, with regions corresponding to different tissue properties. This slide comprehensively outlines the process of utilizing prior knowledge to create a region under test, RUT, for investigating internal structures, such as the brain, through the principles of electromagnetic wave scattering. It demonstrates how both physical and electrical parameters are integrated into the system to enable the precise reconstruction of images that can reveal internal tissue characteristics and potential anomalies. At the top left, we see the microwave imaging setup, where multiple antennas are arranged around a human head model. These antennas emit microwave signals that penetrate the head and interact with the tissues inside. As these signals propagate through the head, they are scattered by different tissue types, and the antennas capture the scattered waves from various angles. The positioning of the antennas ensures that the entire region of interest within the head is covered, providing a rich dataset of signals. The central coordinate system, marked on the head model, defines the axes along which the signals propagate and the locations where measurements are taken. This setup allows the system to measure how electromagnetic waves interact with different tissues, producing what is known as scattering parameters or S-parameters. The graph labeled measured signals at the bottom left illustrates how these scattering parameters vary over a range of frequencies. Each curve in the graph represents the transmission coefficient between two antennas, indicating how much of the transmitted signal was scattered or absorbed by the tissues at different frequencies. This information is critical, as it reflects the electromagnetic response of the brain tissues, helping to differentiate between various tissue types or detect abnormalities. These measured signals form the foundation of the image reconstruction process, as they capture the interaction of microwaves with internal structures. Next, we focus on the physical and electrical parameters that are essential for constructing the imaging space. The physical parameters include the 3D focal points where the signals converge, the radius of the region being imaged, the resolution of the system, and the number and location of antennas. These parameters define the geometry of the imaging space and the precision with which it can capture details. On the electrical side, parameters such as the frequency range, the scattering and reflection coefficients, and the channel numbers and positions, whether monostatic or multistatic, are crucial for mapping the space and extracting meaningful data. Together, these parameters determine how the system interacts with the medium being scanned, in this case, a brain phantom, ensuring that the imaging system can capture accurate and detailed information. Moving to the right side of the slide, we see a representation of the sensor points arranged around the investigation domain. These sensors capture the scattered waves as they propagate through or reflect off the tissues inside the region of interest. The scattered waves contain information about the internal composition of the brain, as different tissues scatter electromagnetic waves in distinct ways. The goal of the imaging process is to gather this scattering information and use it to reconstruct an image of the internal structures. The diagram at the bottom right shows the focal points within the region of interest, which are essential for the confocal microwave imaging technique. These focal points represent specific locations where the electromagnetic signals from different sensors converge, allowing for a detailed analysis of the tissues at those points. Before the confocal algorithm is applied, it is crucial to determine the effective permittivity of the region being scanned. Permittivity describes how an electromagnetic field interacts with the material, and selecting the correct value is vital for accurate image reconstruction. By optimizing the permittivity, the system can more precisely map the interaction between the microwaves and the tissues, leading to better imaging results. In summary, this slide visually and technically demonstrates the entire process of region creation and imaging based on prior knowledge. The measured scattering parameters from the antennas, combined with the physical and electrical properties of the imaging setup, form the foundation for constructing the region under test. This step is crucial for solving the inverse problem in later stages of image reconstruction, where the scattered data will be processed to produce high-resolution images of internal structures like the brain. Through this detailed and methodical approach, the imaging system can accurately identify tissue anomalies, such as targets, making it a valuable tool in non-invasive diagnostics. This slide is an overview of advanced methods in microwave imaging, focusing on two major areas: boundary estimation and effective permittivity estimation. It presents the underlying principles, equations, and visual representations related to each concept, helping explain how electromagnetic waves are used to image and analyze tissues. For boundary estimation on the left, the slide introduces two key formulas for estimating boundaries within the head using microwave imaging techniques. Time delay formula calculates the total time delay for electromagnetic waves to travel through multiple layers of tissue. Each layer has a thickness, d, and a relative permittivity, epsilon I. The time delay depends on the speed of the waves through each layer, which is influenced by the permittivity. The longer the delay, the deeper or more resistive the tissue, giving us clues about where tissue boundaries might exist. Reflection coefficient formula expresses the reflection coefficient gamma, which quantifies the proportion of the electromagnetic wave that is reflected when the wave encounters a boundary between two tissues with different permittivity values. Larger differences in permittivity between adjacent layers cause stronger reflections, signaling the presence of a boundary. In the center of the slide, there are two images visualizing the boundary estimation process. The first diagram, head boundary estimation using scattering signals, shows how electromagnetic signals emitted by antennas around the head are reflected from boundaries. These signals provide data to detect the location of the boundaries within the head, e.g., skin, skull, brain matter. The second diagram, confocal microwave imaging, demonstrates the layering of tissues in the head, including skin, skull, and brain, with detected boundaries highlighted. This process relies on the delay-ansum algorithm to aggregate signals and detect sharp changes in permittivity across the layers. The bottom half of the slide focuses on how effective permittivity is estimated to better understand the internal properties of the tissues. Effective permittivity formula estimates the effective permittivity epsilon EFF at a given point inside the head, accounting for the distance r from the boundary and the overall radius a to the center. The maximum permittivity epsilon max and the constant alpha represent how the permittivity gradually changes as the signal travels deeper into the head. Averaging permittivity over angles averages the permittivity values over multiple angles phi I, which improves the accuracy of imaging by capturing permittivity changes from different perspectives around the head. Visual aids in this section further illustrate how effective permittivity is computed. The image of tissue layers, skin, fat, muscle, inner tissues, shows the electromagnetic wave propagation paths and how the waves interact with different tissues. The scattering data collected by the receivers helps calculate the effective permittivity at different layers. The graph on the right, permittivity versus depth for different entry angles, displays how permittivity changes with depth for different angles: 0 degrees, 90 degrees, 180 degrees, 270 degrees. This demonstrates how permittivity decreases as the waves penetrate deeper, which is critical for reconstructing an accurate image of the internal tissue structure. In summary, this slide explains how boundary estimation and permittivity estimation are combined to enhance microwave imaging, allowing for better detection of tissue boundaries and more accurate reconstruction of internal head structures based on the varying permittivity of different layers. In microwave brain imaging systems, understanding and calculating time delays is essential for creating accurate images of the brain's internal structures. The time delay refers to the duration that electromagnetic waves, transmitted from an antenna, take to travel through different tissue layers, reflect off abnormalities like targets, and return to the receiving antenna. This process hinges on the electromagnetic scattering mechanisms within the body, which are affected by tissue properties like permittivity and conductivity. As microwaves propagate through the brain, they encounter various boundaries such as skin, skull, and brain tissue. These boundaries produce different types of wave responses. Specular reflections occur at the surface of tissues, where the waves bounce off at the same angle as they hit. Creeping wave resonant responses arise when the waves wrap around small objects like targets, which have unique resonant properties that differ from surrounding tissues. The time delays associated with these responses provide critical information for distinguishing between different tissues and abnormalities. The monostatic time delay, when the same antenna transmits and receives, caused by the antenna's physical characteristics tau and the width of the transmitted pulse, tau p. In bistatic channels, where separate antennas are used for transmission and reception, the time delay equation includes an additional term for the distance between the TX and RX antennas. In addition, creeping waves are waves that travel around the surface of an object, such as a target or another scatterer, due to diffraction. These waves are important in imaging systems when the object is smaller than the wavelength of the incident microwave signal. The creeping wave takes a longer, curved path around the object compared to the direct reflection in specular reflection. For creeping waves in a bistatic scenario, the time delay formula would need to account for the additional time the wave spends traveling along the surface of an object, like a tumor, before reaching the receiving antenna. As the waves pass through different layers of tissue, the velocity of the wave changes according to the tissue's permittivity epsilon. The time delay in each medium is the distance through the medium, and Vm is the velocity of the wave in that medium. Since different tissues, skin, skull, brain, have distinct permittivity, the wave speed varies, causing changes in the time delay. The total path delay considers the complete journey of the electromagnetic wave from the transmitting antenna to a focal point in the brain and back to the receiving antenna. This delay is crucial for forming images in microwave imaging systems. In the equation, BI and BJ represent the boundary points along the propagation path, and PF is the focal point inside the brain, where the tumor or other abnormality is located. The refractive indices NM and NB and the speed of light are also factored in to calculate how the signal propagates through different layers. Using Fermat's principle, the system identifies the shortest electrical path, which ensures that the microwaves travel the most efficient route between the TX and RX antennas and the focal point. This principle improves the accuracy of the beam-forming process, which combines signals from multiple antennas to create a focused image of the brain. In the right bottom side, the two graphs at the bottom right illustrate how a microwave signal evolves as it interacts with different media and the target. These graphs show the signal's behavior as it propagates through the medium, reflects off the target, and returns to the receiver. In the left graph, the first notable feature is the early time response, ETR. This part of the signal occurs early in time, representing the initial reflection from the target. ETR is critical as it typically provides the most direct information about the target's location and surface properties. It indicates the earliest wave reflections, which arrive at the receiver soon after transmission. In imaging systems, ATR is crucial because it corresponds to the first encounter of the signal with the target, making it the most accurate representation of the target's position and surface structure. LTR represents the tail end of the received signal, typically consisting of secondary reflections or waves that have traveled through more complex paths, such as multiple scattering events or deeper layers within the target. These later signals may carry valuable information about the internal structure or the material properties of the target, but they are often more attenuated and harder to interpret. LTR can also include effects from the surrounding medium, such as waves creeping along surfaces or resonating inside cavities. The right graph further expands on the complexities of signal behavior, focusing on specific peaks and regions within the signal that help to interpret different phenomena. One key feature is the skin effect, which represents the attenuation and broadening of the signal as it passes through a lossy medium, such as biological tissues or a conductive material. The skin effect results in a decrease in signal amplitude, causing the wave to spread out over time. In the graph, this effect is seen as a gradual decrease in the signal strength after the initial peak. The skin effect can also introduce delays and reduce the sharpness of the reflection, making it harder to pinpoint the target. Another critical region is the occurrence of clutters in the signal. These are unwanted reflections from surrounding objects, noise, or equipment, which create additional, often smaller peaks that do not correspond to the actual target. Clutter can complicate signal interpretation, as they may overlap or obscure the primary signal from the target, potentially reducing the imaging system's accuracy. In the graph, clutter signals appear as small, irregular oscillations after the main reflection. Proper signal processing techniques are needed to filter out these clutters to focus on the target signal. Finally, the target reflection is the most critical peak in the signal. This distinct peak represents the actual desired reflection from the target. It occurs at a specific time, corresponding to the moment when the transmitted microwave signal reaches the target, reflects, and returns to the receiver. The time delay associated with this peak provides essential information about the target's distance from the system, while the amplitude of the peak reflects the strength of the reflection, which can be used to infer the material properties of the target. A clear and strong target signal is necessary for accurate imaging, and the position of this peak is crucial for determining the target's exact location. In summary, these two graphs demonstrate the complex interplay between early and late signal responses, signal attenuation due to the skin effect, and the challenges posed by clutter. The target reflection remains the most significant feature, and accurately isolating this peak from the rest of the signal is key to successful microwave imaging. Through careful analysis of the ETR, LTR, and signal peaks, an imaging system can construct a detailed representation of the target, even in the presence of noise and multiple wave interactions. This slide presents a detailed overview of advanced artifact removal algorithms used in microwave imaging techniques, specifically focusing on calibration-based artifact suppression to enhance brain imaging accuracy. These methods are critical in non-invasive diagnostics, as they help ensure that reflections and artifacts, such as skin clutter or environmental noise, do not interfere with the imaging of deeper brain tissues. By implementing these techniques, medical professionals can identify tissue anomalies, such as tumors or abnormalities, more accurately. The slide divides artifact removal techniques into two broad categories: data-independent filtering and adaptive filtering. Both approaches aim to minimize unwanted reflections and noise, thereby enhancing the quality of the reconstructed image and improving diagnostic capabilities. In the data-independent section, several specific methods are demonstrated, each aiming to suppress clutter without relying on real-time data adjustments. The ideal differential subtraction method subtracts a reference head model signal, BR, from the current brain scan signal, BI, to remove known artifacts. The difference between the reference and real-time scans eliminates the constant skin layer effect, revealing deeper tissue structures more clearly. In average subtraction, the skin clutter is reduced by subtracting the average value of the received signals, removing repetitive patterns across multiple measurements. The rotation subtraction technique uses a rotating platform to collect signals from multiple angles. By comparing the signal BR from different rotational positions, artifacts can be minimized. The subtraction of signals at various rotational points helps isolate the brain tissue signal from clutter. The adaptive filtering section focuses on real-time adjustments to optimize clutter and noise suppression. The Wiener filter adapts its parameters to minimize the mean square error between the received signal and the desired target signal. It uses surrounding signal information, BPNN, and minimizes the error through optimization of the filter coefficients, Q. This method is highly effective at filtering out noise and unwanted signals dynamically. The entropy-based time window method suppresses clutter by analyzing the entropy of the signal over time. When the entropy exceeds a certain threshold, clutter is removed by applying a windowing function that zeroes out high-entropy segments of the signal. The entropy function measures the randomness in the signal and helps identify parts of the signal dominated by noise or clutter, allowing for more precise imaging. Let's dive into the 4 architectures depicted in this slide, all designed for qualitative electromagnetic brain imaging. Beamforming is a crucial technique used in qualitative electromagnetic imaging to focus signals from multiple antennas to a specific point in space. In the context of qualitative electromagnetic imaging like confocal imaging, the process can be broken down into several key steps, each serving an important role in forming a clear image of the target, such as in brain imaging or other complex tissues. The key aspect across all these beamformers architectures is the spatial and temporal variability of the weights and filters, allowing for enhanced adaptability and precision in processing the measured scattering parameters, S parameters. This variability is crucial for capturing accurate and high-resolution images of the brain. Delay and sum beamformer is the simplest beamforming method. In this architecture, signals, S parameters, received by multiple antennas are aligned using time delays. These delays ensure that signals from a particular direction or region of interest are in phase, and then they are summed to create a focused signal. The time delays are applied spatially depending on the target region, and these can change over time if the region of interest changes dynamically. However, this architecture lacks the complexity and fine control of more advanced methods. Ideal for imaging larger structures or areas with relatively stable conditions, but it has limited precision in detecting smaller or more subtle abnormalities. Group focus FIR beamformer architecture enhances the basic delay and sum method by applying finite impulse response (FIR) filters to the signals. The filters help control the focus across groups of signals, improving the system's ability to focus on specific regions. The FIR filters and beamforming weights vary spatially to target different groups of regions within the brain. Temporally, the filters can adapt to shifting focus areas or changing conditions, such as moving blood or tissue. Useful for improving spatial resolution and focusing on specific groups of tissue. It allows the imaging system to handle more complex scenarios than delay and sum. Dynamic focus FIR beamformer architecture introduces dynamic focusing, where both the time delays and FIR filters are continuously adapted in real time. This dynamic focus enables the system to track changes in the brain structure or activity, such as moving tissue or active regions. The system dynamically adjusts both the spatial focus and the FIR filters over time, providing real-time adaptability. As brain structures change or activities occur, the system recalibrates to maintain optimal focus. Ideal for real-time applications, such as monitoring during brain surgery or observing dynamic physiological processes. It offers superior flexibility and precision in capturing real-time changes. Spatial matched filter beamformer method uses matched filters to align with the expected signal patterns from specific regions of the brain, maximizing sensitivity to specific targets. Matched filters are designed based on known characteristics of the tissue or anomalies, such as tumors or lesions. The matched filters are both spatially and temporally variant, as they need to adapt to the specific locations and conditions being imaged. The filters can change over time if the target signal characteristics evolve or if the focus shifts. Extremely useful for detecting subtle abnormalities, such as small tumors or lesions, by enhancing the system's sensitivity to these specific regions. It is particularly valuable in diagnostic settings where high precision is required. Spatial matched filter maximizes sensitivity to specific brain structures or anomalies, providing the highest precision for diagnostic imaging. This slide presents a comprehensive demonstration of the impact of different steps such as clutter suppression, time delay arrangements, and advanced beamforming techniques for the reconstruction of brain tissue images. Starting with the graph in the top left, we see amplitude versus time plots that display the evolution of signals over time, measured in nanoseconds. Multiple signals, represented by different colors, likely correspond to data from various sensors or antenna positions in a multi-static radar system, where multiple transmitters and receivers are used. The purpose of this graph is to demonstrate how artifacts can be removed from the signals to improve image clarity. It contains time domain signals with and without artifact removal. The signals are displayed in different colors, red, blue, green, showing how the waveforms change after processing. Initially, the signals contain noise or unwanted reflections, which make it difficult to isolate the object of interest. However, after applying the artifact removal techniques, the signals are cleaner, and the object's response is more prominent. This section emphasizes the importance of artifact removal in achieving clearer, more accurate signals that can be used for reliable imaging and detection. In the bottom left corner, two images are shown side by side, comparing results with and without artifact removal. The left image, without artifact removal, shows significant noise or clutter, which obscures the object or target that the system is trying to detect. This could represent an object such as a tumor in a medical imaging system, where the signal reflections from surrounding tissues introduce unwanted artifacts. On the right, after artifact removal, the image is much cleaner, with the object clearly visible. This visual contrast demonstrates the effectiveness of artifact removal techniques, which are designed to clean up the image by filtering out unwanted signals and focusing on the reflections directly associated with the target. In the top right section, the diagram illustrates a process where signals are time-shifted and then summed. The top part of the diagram shows the geometric relationship between the antennas and the object being imaged, highlighting how different antennas receive signals at different times due to varying distances. Each received signal is individually time-shifted to account for these propagation delays, ensuring that the signals align properly when they are summed. This summation is key to enhancing the signals related to the object of interest while reducing background noise or clutter, thus improving the overall image quality. In the bottom right corner, we see a workflow diagram that details the steps involved in improving the image quality through artifact removal. The process begins with hybrid artifact removal, a combination of different techniques aimed at eliminating unwanted signals. This is followed by multi-static artifact removal, where artifacts are removed in a system that uses multiple transmitters and receivers. Additionally, monostatic imaging, where a single antenna acts as both the transmitter and receiver, is included in the process. Finally, the workflow converges in the combined multistatic and monostatic imaging (CMM) approach, where both techniques are utilized together to enhance the final image. The images shown to the right of this workflow demonstrate the success of these methods, with improved clarity and resolution in the final image. Overall, the slide presents a complete workflow for improving signal and image quality in a radar or microwave imaging system. By comparing raw signals and images before and after artifact removal, it highlights the critical role that signal processing plays in enhancing the visibility of objects within the scanned medium. Techniques such as beamforming, hybrid artifact removal, and combined multistatic and monostatic imaging are essential for reducing noise and clutter, ensuring that the final images are as clear and accurate as possible. After time aligning the signals from multiple antennas, the signals are summed together to enhance the signal coming from the desired location, which is known as focusing algorithm of coherent integration. The goal is to enhance the response from the desired location and suppress noise and interference from other areas. The process essentially reinforces signals that come from the focal point, leading to a clearer image. In this slide, we compare 6 imaging algorithms used for breast cancer detection, each visualized with its respective performance. Let's walk through them, focusing on the key differences in resolution, noise suppression, and interference rejection, while also introducing the core mathematical formulations behind each method. First, we have adaptive microwave imaging, MAMI, which is the most advanced method shown here. MAMI operates in two stages, using a robust Capon beamforming approach. The intensity which demonstrated by E is calculated by summing the backscattered energy, weighted to reduce noise and interference. You can see the clear detection of the target with high resolution and minimal noise. Its formula is displayed in the right hand, where W is the adaptive weight vector. MAMI's precision stands out, offering excellent clarity with almost no clutter around the target. Next, the multistatic delay and sum (DAS) method extends the concept by using multiple antennas for signal acquisition. It performs slightly better than the monostatic version, but still suffers from significant noise and interference, resulting in poor target localization. The intensity is demonstrated by I moving to the robust Capon beamforming (RCB) method. This technique aims to minimize interference while maintaining signal fidelity by optimizing the weight vector. Its intensity formula is IRCB, where R is the covariance matrix and H are the steering vector. RCB provides a high-resolution image, but shows some background interference, though still effective at localizing the target. The amplitude and phase estimation (APES) method focuses on both amplitude and phase recovery of the backscattered signals, offering higher resolution. However, its sensitivity to noise can reduce the quality of the output. The intensity formula is I-APES. APES performs similarly to RCB, but with slightly more noise, though it still achieves high-resolution imaging. In contrast, monostatic delay and sum is a simpler approach that sums signals after time shifting to align them. In its formula, tau I is the time delay. As shown, monostatic DAS struggles with heavy noise and low resolution, making it hard to distinguish the target clearly. Lastly, we have microwave imaging spacetime, MIST, which applies spacetime beamforming to process signals. While it offers some interference suppression, it results in lower resolution and higher clutter compared to the adaptive methods. The intensity formula here is I MIST, with W representing the weight vector and Xi the received signal. As you can see, the MIST method provides the least clear image, with significant clutter making target detection more challenging. In summary, MAMI and RCB stand out for their high-resolution images and excellent noise suppression, making them the preferred choices for microwave imaging. On the other hand, the simpler DAS methods, despite their computational ease, struggle with interference and poor resolution. APES offers competitive resolution but remains sensitive to noise, while MIST shows its limitations with low clarity and higher interference. Each method presents trade-offs, but overall, MAMI provides the best results in target detection. Electromagnetic imaging is an ill-posed inverse problem whose solution is usually computationally expensive. Nonlinearity comes from complex interactions between the measured EM field and the material parameters. The ill-posedness arises from multiple scatterings, insufficient measurements, and noise corruption. Due to multiple scatterings of EM waves, a slight variation of targets may change the EM field substantially. In most cases, we only transmitting antenna receiving antenna measurement record the field at specific locations, i.e., the field samples are sparse in space. The attenuation of EM fields caused by diffraction and absorption of media, as well as a noisy environment, further increases the ill-posedness. Solving EM imaging problems often requires accurate modeling of EM wave propagation in the DOI. This process is called forward modeling and is implemented by numerical algorithms such as the finite element method. However, it is computationally intensive, especially for large DOIs. Machine learning, ML, techniques and especially deep learning, DL, show potential in fast and accurate imaging. However, the high performance of purely data-driven approaches relies on constructing a training set that is statistically consistent with practical scenarios, which is often not possible in EM imaging tasks. Consequently, generalizability becomes a major concern. On the other hand, physical principles underlie EM phenomena and provide baselines for current imaging techniques. To benefit from prior knowledge in big data and the theoretical constraint of physical laws, physics-embedded ML methods for EM imaging have become the focus of a large body of recent work. This video surveys various schemes to incorporate physics in learning-based EM imaging. We first introduce background on EM imaging and basic formulations of the inverse problem. We then focus on different types of strategies combining physics and ML for linear and nonlinear imaging and discuss their advantages and limitations. Our aim is to facilitate the study of intelligent EM imaging methods that will be efficient, interpretable, and controllable. In this slide, we explore machine learning, ML, and deep learning solutions for addressing the inverse electromagnetic, EM, scattering problem, which involves retrieving the permittivity of dielectric scatterers from measured scattering data. In electromagnetic imaging, particularly for brain imaging, the problem is often approached as a combination of source and scattering problems. This problem involves determining the permittivity epsilon of dielectric scatterers from the measured scattering data. Electromagnetic brain imaging devices use multiple antennas to transmit and receive high-frequency electromagnetic waves into the brain, which interact with brain tissues, and the scattered field will be received in antenna. These interactions cause scattering due to differences in the tissue's electromagnetic properties. In scattering theory, the problem is described by the Lippmann-Schwinger integral equation, which relates the total field to the incident and scattered fields. The scattered field is expressed as the integral of the source, Green's function, and contrast function, which forms our forward model. To solve this problem, we employ an iterative method that utilizes the Born approximation at each step. During the kth iteration of this method, the total field ATOC-1 is computed for the contrast function chi-k-1 obtained in the previous iteration, using the state equation. By substituting ATOC-1 into the data equation and applying the Tikhonov regularization method, the optimization problem is solved to obtain chi-k. For the first iteration, chi0 is chosen arbitrarily. The slide presents the formulation associated with this solution, including the closed-form solution. The scattering model G, which is typically nonlinear due to the multiple scattering interactions, makes traditional iterative approaches computationally expensive and time-consuming. Traditional methods, such as the Born iterative method and contrast source inversion, require iterative optimization with heavy computational cost. Due to the time-consuming nature of these iterative methods, we need faster techniques. With advancements in deep learning, particularly convolutional neural networks, CNNs, we have the potential to solve inverse scattering problems in real time, offering faster reconstructions without sacrificing accuracy. CNNs learn a mapping epsilon hat equals GS, where epsilon hat is the predicted permittivity from the scattering data. CNNs are well suited to handle the spatial complexities of EM scattering, bypassing some of the challenges associated with conventional iterative techniques and provide real-time solutions. This approach is particularly promising for achieving real-time imaging solutions. In more details point of view, the CNN combination with UNet architecture can be divided to different training schemes for solving inverse scattering problems. One of them is direct inversion. This scheme uses CNN to directly map scattering data to the permittivity distribution without integrating additional physics constraints or models. 2. Backpropagation, a more conventional approach where the neural network learns through optimization using backpropagation. In this scheme, CNN training is performed using backpropagation with physics-informed loss functions, which may include Tikhonov regularization, improving the inversion process by penalizing unrealistic solutions. 3. Dominant current scheme, DCS. DCS emphasizes the dominant current contributions in the inversion process. The dominant current ID can be obtained by singular value decomposition, SVD, of the forward model matrix G. This approach allows for faster and more accurate computations. In addition, a key aspect of the artificial intelligence-based approach is how physics is incorporated into the ML models. 3 strategies are highlighted as shown in the right side of the slide. 1. Learning after physics processing. In this approach, physics-based models are used to pre-process the input data for ML models, ensuring that the data passed to the neural network is physically meaningful, which can guide the model toward more accurate solutions. Here, the data pre-processing involves applying a physics-based model to obtain an initial estimate of epsilon. This pre-processing helps to set a physically meaningful input for the ML model. 2. Learning with physics loss. Here, physics knowledge is embedded directly into the loss function of the neural network. This might involve adding regularization terms or physical constraints, such as Tikhonov regularization, to guide the network in producing physically consistent solutions. The Tikhonov regularization technique plays a vital role in stabilizing the inversion process by adding a penalty for overly complex solutions, thus ensuring the smoothness of the reconstructed permittivity profile. This regularization is crucial for mitigating the ill-posed nature of inverse problems and preventing overfitting, especially when dealing with noisy or incomplete data. 3. Learning with physics models. The final approach uses physics-based insights to shape the architecture of the ML model itself, ensuring that the network structure respects known physical laws and relationships, which improves the model's ability to generalize and produce meaningful predictions. For instance, the network might be designed to inherently respect conservation laws or other physical principles, optimizing the structure to align with these constraints. Combining deep learning with physics-informed ML methods offers a promising approach to inverse EM problems. This integration facilitates rapid and accurate solutions, significantly reducing computation times compared to traditional methods. The potential applications are extensive, including medical diagnostics, geophysical exploration, and non-destructive testing, where real-time quantitative imaging is crucial. The synergy between advanced deep learning techniques and physics-based insights represents a major step forward in addressing the computational challenges associated with conventional iterative algorithms. The direct inversion method in AI-powered electromagnetic imaging represents a promising approach to solving the complex inverse electromagnetic scattering problem in brain imaging. The core objective of this method is to reconstruct the internal properties of the brain, particularly the permittivity profile, a measure of how the brain tissue interacts with electromagnetic waves, by analyzing the scattered electromagnetic fields that result from incident waves passing through the brain. The inverse scattering problem is inherently difficult due to its ill-posed and nonlinear nature. This means that small changes in the scattered wave data can lead to large uncertainties in the reconstructed brain images, making traditional mathematical approaches less effective. The direct inversion scheme in AI-powered electromagnetic imaging presents a promising solution for the inverse scattering problem in brain imaging. It offers a fast, direct approach for reconstructing brain structures from scattered electromagnetic fields using deep learning, with the potential for real-time medical imaging. However, for more complex cases, complementary or more sophisticated techniques may be required to enhance accuracy and precision. However, the integration of AI-powered solutions like deep learning offers a more robust and reliable alternative to this challenge. Before diving into the inverse problem, it is essential to understand the forward scattering problem, which involves solving the electric field integral equation, EFIE. This equation describes how incident electromagnetic waves interact with the brain tissue, producing scattered fields. These scattered fields are measured by antennas or sensors positioned around the head. The forward problem assumes that the internal properties, such as permittivity, of the brain are known, and the task is to predict how waves will scatter. Numerical methods like the method of moments, MOM, finite element method, FEM, and finite difference time domain, FDTD, are commonly used to simulate the forward scattering problem. In addition, this analysis can be done by electromagnetic wave software like CST Studio, HFSS, and FICO. These simulations generate scattering parameters, S-parameters, which represent how electromagnetic waves scatter based on the material properties of the brain. This data is essential for creating a comprehensive training set for the AI model. By this way, we can generate databases to train the AI-based model, such as convolutional neural network, CNN. CNN has been trained on a large dataset that links known permittivity distributions with their corresponding scattered fields. During the training phase, the network learns the intricate relationships between the scattered field measurements and the underlying internal properties of the brain. The direct inversion scheme offers a fast and simplistic approach to solving the inverse scattering problem by employing a convolutional neural network, CNN, to directly map the scattered fields to the internal brain structures. The inverse scattering problem flips the process. Instead of predicting how waves scatter from known internal properties, the goal is to reconstruct the unknown internal properties of the brain, specifically, the permittivity profile, from the scattered wave data. In the context of brain imaging, this is particularly challenging due to the complex nature of brain tissue and the nonlinearity of the problem. The scattered wave data alone is insufficient to reconstruct accurate images, without sophisticated algorithms capable of dealing with these complexities. In this scheme, the scattered electromagnetic fields, captured as S-parameters by the sensor array around the head, are directly input into a pre-trained CNN. CNN processes the input data by passing it through multiple convolutional layers, where the network automatically learns to detect patterns and features in the scattered field data that correspond to different permittivity profiles. The final output of the network is a reconstructed image that represents the internal permittivity distribution of the brain. This approach bypasses the need for traditional iterative algorithms that often struggle with nonlinearity and noise in the data, allowing for a more real-time or near-instantaneous reconstruction of the brain's internal structures. While the direct inversion scheme, DIS, is computationally efficient and fast, it does have limitations in terms of accuracy, especially when dealing with complex or highly nonlinear profiles. The model's effectiveness relies heavily on the quality and diversity of the training data, as well as the network's ability to generalize from this data to unseen cases. For simple or linear scattering environments, DIS can provide acceptable results. However, for more complicated scenarios, such as those involving strong scatterers or intricate structures within the brain, the method may struggle to achieve the desired accuracy. Since the convolutional neural network, CNN, directly maps the input data, scattered electromagnetic fields, to the output, permittivity profiles, there is no need for the iterative, computationally intensive processes often required in solving inverse problems. This makes direct inversion scheme, DIS, particularly valuable for real-time applications, such as emergency brain imaging during critical medical events like strokes, where rapid diagnosis is crucial. However, the simplicity of DIS also presents challenges. The nonlinear nature of the inverse scattering problem means that basic direct inversion might struggle to accurately capture the intricate details within the brain, especially in complex scattering environments or when dealing with heterogeneous tissue structures. In this slide, we introduce some advanced techniques to enhance the performance of DIS. Specifically, we focus on the backpropagation scheme, BPS, which is highlighted on the left side of the slide. BPS improves accuracy and robustness by incorporating additional steps, either before or after the CNN processes the data. This helps overcome the limitations of straightforward direct inversion. Although it is possible to train a CNN to directly regress from the measured scattered fields E_S to relative permittivity εr, the learning process can be simplified by first performing non-iterative inversion algorithms before training. BPS is one such method based on CNNs, designed to address the inverse scattering problem with enhanced precision. The key idea behind BPS is that the induced current IB in the scattering medium is proportional to the backpropagated field, which is highly effective for reconstructing weak scattering objects. The mathematical representation of this process is demonstrated in each step. The BPS workflow improves the reconstruction of permittivity profiles by considering the interaction between the induced current and total field, particularly for weak scattering objects. By combining the information from all incident fields, the least squares solution is computed for each element of the contrast. This refined contrast information is then fed into the CNN as the input, while the outputs are the true contrasts for the domain. BPS is applicable for arbitrary incidence fields and is effective for both near and far field measurements, setting it apart from traditional methods like filtered backpropagation, FBP, in diffraction tomography. It's essential to distinguish the backpropagation in BPS from the error backpropagation algorithm used in CNNs for updating weights. The backpropagation in BPS refers to the physical propagation of electromagnetic fields, whereas in CNNs, it refers to the computational process of optimizing the network. BPS enhances the accuracy of inverse scattering solutions, especially for complex media, by using an intermediate backpropagation step before feeding the data into the CNN. This makes it a robust method for reconstructing fine details in medical imaging applications, like brain scans, where time and precision are both critical. In addition, on the right side, we can see the data preprocessing structure, which plays a crucial role in preparing the original FDTD signal data for the deep learning model. This section ensures that the raw data generated by the FDTD solver, consisting of time-domain electromagnetic signals, is correctly transformed into a format that the neural network can process efficiently. The data preprocessing phase takes the original signal map and applies steps such as downsampling and normalization to compress and standardize the data. This step is critical because it bridges the gap between the complex FDTD simulations and the deep learning phase, ensuring that the data is efficiently utilized for training. Following this is the post-processing structure, where we aim to further improve the imaging performance of the FCERNN using UNet, an image optimization module. UNet, a well-known deep learning architecture for biomedical image segmentation, is employed here for refining the results generated by the 3D FCERN. The UNet architecture, with its downsampling and upsampling components, processes the 2D slices of the brain reconstruction results from the FCERNN and produces the final inversion results with improved resolution and accuracy. The downsampling part extracts both global and local features from the images using convolutional and pooling layers, while the upsampling part restores the segmented maps back to their original size, ensuring uniform color difference and feature preservation. Additionally, the skip concatenate connections between corresponding layers in the downsampling and upsampling parts allow for better feature reuse, thereby enhancing the model's ability to produce more accurate and detailed reconstructions of the brain tissue. In essence, this slide presents a complete picture of the data processing workflow, starting from raw signal preprocessing, moving through deep learning-based reconstruction, and ending with UNet-based post-processing for final optimized imaging results. PINs represent a novel approach to solving inverse problems by incorporating physical laws directly into the structure of a neural network. This hybrid framework allows the neural network to respect the constraints imposed by the underlying physics, improving accuracy and reducing the need for large amounts of training data. In inverse EM problems like microwave brain imaging, the PDEs governing Maxwell's equations form the basis for how electromagnetic fields interact with different materials, e.g., brain tissue, blood. These equations can be solved using a variety of discretization schemes like the finite difference method, FDM, finite element method, FEM, or spectral methods, SM. The discretization schemes transform continuous PDEs into a form that can be handled by the network, making them applicable to domains like the head where complex structures and geometries exist. The slide illustrates this transformation, where the integral and differential equations are applied to real-world problems using these discretization techniques. Simultaneously, automatic differentiation (AD) allows the PINN to compute derivatives of complex quantities directly, improving the network's ability to backpropagate gradients during training. This combination of discrete and analytical methods is critical for solving inverse EM problems, where one must infer the unknown permittivity and conductivity profiles inside the brain from observed scattered fields. The flowchart illustrating forward and backward propagation shows how PINs process input data through a neural network in stages, first predicting intermediate quantities such as scattered fields and contrast sources, forward pass, and then using backpropagation to adjust the model parameters based on error calculations, backward pass. The forward step predicts physical quantities, e.g., electric fields, while the backward pass uses error gradients to adjust the network to better match the measured data. For instance, in microwave brain imaging, the forward process computes how microwaves scatter when interacting with brain tissue, while the backward pass uses this information to refine the model's internal parameters, permittivity and conductivity values. In PINs, the loss function incorporates not only traditional data-driven loss, i.e., how well the network's output matches the observed data, but also physics-based losses derived from the governing PDEs. This dual approach ensures that the model respects physical laws while also fitting the experimental data. The loss function combines the mean squared error, MSE, between predicted fields and measured data with the MSE of the governing PDEs, allowing the model to optimize both aspects simultaneously. The total loss is minimized using optimization algorithms, leading to improved model accuracy and stability, especially in inverse problems where data might be scarce or noisy. This slide highlights how physics-informed neural networks are applied to the inverse electromagnetic scattering problem in microwave brain imaging, addressing the process through three key stages: integral, differential, and simultaneous methods. This slide emphasizes the roles of the integral, differential, and simultaneous methods in the PINN framework for microwave brain imaging, and how they contribute to the overall process of real-time brain image reconstruction. The key idea here is the simultaneous use of forward and inverse processes within the neural network. The integral formulation, top left equation, captures how the brain's material properties, such as permittivity, affect the electromagnetic fields in the forward process. The equation represents the total electric field, E, as a combination of the incident field and the scattered field, which is integrated over the entire volume of the brain. The forward process uses this integral approach to predict how microwaves interact with the brain tissues, resulting in scattered fields detectable by external sensors. The neural network computes the contrast source, J, and the electric field, E, based on an initial guess for the brain's permittivity. These predictions guide the model in simulating the interaction between microwaves and the complex anatomy of brain tissues. The differential formulation, top right equation, is essential for capturing the local variations in electric and magnetic fields within the brain, governed by Maxwell's equations. The differential equations describe how the electric field, EZ, and magnetic fields, HX, high, evolve over time and space, accounting for the influence of permittivity and permeability in the brain tissues. This method is crucial for simulating the intricate dynamics of electromagnetic wave propagation through different types of brain tissue: white matter, gray matter, cerebrospinal fluid, etc. The recurrent neural network, RNN, uses these differential equations to calculate the fields at each time step, employing finite differences to approximate the partial derivatives, which ensures that the evolving wavefronts and field interactions are accurately simulated. The simultaneous method, illustrated in the lower diagrams, integrates both forward and inverse processes within the neural network to refine the brain model iteratively. The forward process, shown in green, calculates the wave propagation based on an initial estimate of the brain's properties, while the inverse process, in blue, works to update the permittivity by using measured scattered field data. This dual-process framework ensures that the neural network progressively improves its understanding of the brain's internal material properties, such as permittivity, by comparing predicted and actual measured data in real time. This simultaneous approach, where both forward and inverse processes are interwoven, allows the network to unroll over time, learning how electromagnetic waves scatter and propagate through the brain while continuously refining the model. Each time step in the forward process corresponds to the wave propagation, and the inverse process updates the brain's permittivity by minimizing the difference between the measured and predicted scattered fields. This method enhances the accuracy of the reconstructed image of the brain's internal structures. The final output of the neural network is a reconstructed image of the brain's permittivity distribution, which provides critical insights into the brain's state, such as identifying whether a stroke has caused ischemia, blockage, or hemorrhage, bleeding. By embedding Maxwell's equations directly into the network, PINs provide a robust framework for solving inverse EM problems like microwave brain imaging. The combination of integral, differential, and simultaneous methods within the neural network allows for real-time brain imaging, a breakthrough that can lead to portable, non-invasive imaging systems deployable in emergency rooms or ambulances. These advancements can drastically improve stroke diagnostics by providing fast, accurate, and actionable insights into brain conditions. In this slide, to demonstrate the effectiveness of the deep learning for inverse electromagnetic scattering problems, we put the reconstructed image results from the different papers that cited in the references sections. On this slide, we explore the reconstruction of 3D relative permittivity and conductivity distributions in the human brain using the FCRNN model, along with its enhanced version incorporating UNet. Starting with the left side, we see how the FCRNN model performs the core task of reconstructing both permittivity and conductivity maps. Notice how the 3D structures and 2D slices reflect an accurate representation of the brain's internal tissues, which are compared here to the ground truth. The FCRNN is particularly effective at capturing the overall shape and structure of brain tissues. One of the key advantages of FCRNN is its speed and efficiency. By using a fully convolutional architecture, the model significantly reduces computational complexity, making it ideal for real-time applications. It is also capable of handling high-resolution, high-contrast objects, which is essential in medical imaging of complex structures like the brain. Furthermore, its scalability allows it to manage large domains, such as the full human brain. However, the FCRNN model isn't without limitations. While it reconstructs the general structure quite well, there are some notable inaccuracies along the tissue boundaries. You'll also notice some artifacts and noise, especially in environments with lower signal-to-noise ratios. As we reduce the SNR, these inaccuracies become more pronounced, leading to blurring and misrepresentation of finer tissue details. Now, moving to the right side, we introduce UNet, which plays a significant role in enhancing the results. When combined with FCRNN, UNet focuses on refining the edges of the tissues and eliminating the noise, which greatly improves the clarity and accuracy of the images. Let's look at how UNet enhances performance under varying SNR conditions. At SNR equals 10 dB, where the FCRNN results are visibly noisy and blurred, UNet steps in and cleans up the noise while sharpening tissue boundaries. Even in these challenging conditions, the enhanced model is able to recover critical details that would otherwise be lost. At higher SNRs, like 20 dB and 30 dB, the combined model produces robust, high-quality reconstructions that closely resemble the ground truth, effectively restoring the small but important structures within the brain. In summary, while FCRNN offers fast and scalable reconstructions, it faces challenges with boundary noise and sensitivity to low SNR environments. This is where the inclusion of UNet comes into play, addressing these limitations and providing a more refined and accurate output, particularly in noisy conditions. Together, FCRN and UNet form a powerful solution for real-time electromagnetic brain imaging, offering the potential for high-quality, reliable imaging even under difficult conditions.